Good morning, everyone, or good day for those who are from Europe. My name is Ari Kellenson. I'm a program manager in Seattle transmission and distribution sector. We're just going to wait 5 minutes or so to allow all attendees to be fully registered before we begin, and then we'll start, okay? Thank you for your patience. Hello, Belen from Red Electrica. Let's do a quick sound check.
Hello, yeah. Can you hear me as well?
Yeah, can hear you perfectly. Thank you.
Thank you.
Okay, so good day, good morning, everyone. Thank you for joining us today for part C of this interesting workshop on grid-scale battery energy storage system best practices, looking at international perspectives. We already had 2 sessions. Session A was to cover North American perspectives on grid-scale batteries, looking at utilities, ISO, TSOs, and manufacturers. Session B was Australia and South Korea, and today's session C looking at the European aspect of this interesting event. So, as I said, my name is Ari Kellenson. I'm a program manager in Seattle International, overseeing transmission distribution interest groups or programs. For today's session, as a reminder, we will start by a presentation from Trena Dominica from Italy. Then we will have a presentation from Belen from Red Electrica in Spain. And for the rest of session C1, we will have Bobby Smith, who is the head of energy storage in Ireland. We'll have a general Q&A session to address some of the pending questions from all of these three. And then we will move on to session C2. We will have another 2 presentations there from Fluence and another one from I can't recall right now, but Germany. Yeah, we'll have Germany there. So a little bit about the programs in Seattle. So we in Seattle, we cover vertical power from generation to transmission, distribution, and behind the meter. I highlighted here 3 programs that are most relevant for grid-scale energy battery storage. Starting from the left, energy and integration strategy. This is a program that is looking at strategic planning at the high level. They're looking at grid edge technology, strategy, integration, looking at the entire energy mix. So all various kinds of energy resources and DERs, hydrogen storage, compressed air storage, battery energy storage, and so on and so forth. Really looking at cost-effective ways to integrate energy resources to meet net zero carbon. The second program that I highlighted here is called Distribution Equipment and Planning. These programs are composed of distribution planners and engineers that are looking at line asset management, standards, making sure there's enough hosting capacity. And of course, as electric vehicles are more and more being integrated to the distribution level, they also started to look at grid scale energy storage to improve reliability and safety, for good planning and operation from the distribution sector. The last one on the right-hand side is where this event and project that we're working on actually came from. Transmission planning and operations is a program that is looking at load flow studies, modeling, looking at, interconnection requirements, integrated resource planning, and so on and so forth. We have transmission planners and operators, and battery energy storage came along after having brainstorm discussion that folks mentioned that, it will be very important to see best practices so that they could learn from utilities and from industry that are more advanced from some of the North American parts, especially looking at Europe, California, and Australia. So that's more or less the need for this event. A little bit more about this project. I'll let Dr. Paulo Barbosa to introduce himself and the team, and then we will move on to the presentation, okay? So Paulo, good day, and thank you for being with us.
Good afternoon, good day for everyone. Thanks all speakers who kindly accepted, collaborated with us in this project, in this webinar. Thanks for the audience for being here today. I'd like to say some few words about ICP-Tech, and it was a great opportunity to ICP-Tech collaborate with CIADI in this project. ICP-Tech was founded in 2011 by myself as an energy consulting and R&D firm. We work on several areas of energy sector. I would say in the main components of the supply chain, including generation, transmission, and distribution, and more recently on energy storage issues. We joined this team in order to work on this project that includes myself and Dr. Carlos Davi Barbosa. He's an engineer, doctor in engineering, consulting in the energy area, and also Julian Hunt is a Dr. Phil in engineering science, and he's an expert on energy storage. This webinar is a part of the general project that intends to expand the knowledge and review the state of art on grid scale battery, mainly focused on application. Of course, this is a big challenge for us since battery storage perhaps is at the beginning stage of development. We can discover new technologies, new regulatory and business model, and many market players around the world. And of course, we can foresee an ocean of opportunities and possible benefits to electric grid modernization. Therefore, this webinar represents a significant contribution to this project. And thank you all for collaborating with us and for being here today.
Thank you, Paulo, for supporting us with this project, which, as I said, came from transmission planning and operations. And also we have a survey which we open to anybody who is participating in it, as long as you're a utility, TSO or ISO or battery manufacturers. We will have a poll towards the end of the session, and I will ask if you'd like to participate. So stay tuned for that. Some more details about the project in addition to what Paulo said. As Paulo mentioned, we really wanted to see, best practices across the world when it comes to battery energy storage, and a big part of the project is just a survey. These are the questions that the project is answering, but I think Paulo touched on that, so for the sake of time, let's move on to the first presentation by Domenica. She's an electrical engineer at the Innovation Factory System at Terna. She has technical background in electrical engineering focused on renewable energy, power system management, and energy markets. More than 2 years of experience in energy storage system project called the Storage Lab. So Domenica, it's a pleasure to host you here today with us. I will hand control over to you, and you can take it from there. Let's see. We can see your screen.
Okay.
We can see you.
Hello.
Hello, good day. How are you?
Okay. Hello. Hello, fine. Thank you for inviting me to this interesting event. I just turned on the camera to say hello to you. I'm Domenica Conenna. I work for Terna, the Italian TSO, and today I'm introducing the activity of Terna in the battery storage project. I don't know if you can see my screen.
Yeah, if you can, I don't know in Italian, but if you can do, there you go, full screen. That's perfect, thank you.
Okay. Okay. So my presentation is organized in 3 parts. I will start with a brief introduction to the Italian framework. Then we will discuss about the main results of the test carried out in Terna project. And after that, I will give you some hint about the ongoing activities. So, okay. Maybe, as you know, Terna is the Italian transmission system operator, and so Terna is responsible for the transmission and dispatching of electricity in Italy. On the top of this slide, you can see the, let's say, key factors which pushed Terna to start the activities on energy storage system, or ESS, back in 2011. So the main factors that were starting to have a huge impact on the power grid were obviously the RES growth that also caused the grid congestions and RES curtailment, and also the trend of reduction of reserve margin and grid inertia in the system. So the ESS were one of the available tools which could contribute to support the power grid and let's say guarantee safe and secure operation. So since 2011, let's say in 2011, the storage market was not so developed at let's say large scale, also because there was a limited technical know-how on about the capabilities of ESS. And so Terna, also thanks to the approval of the Italian Energy Authority, decided to start this 2 big project on battery system named Storage Lab and Energy Intensive, and I will give you some details in the next slide. After that, and after several years of experience with also other installation of different ESS technologies, Terna also started a process in order to open the market to ESS, thanks to the launch of several market-based projects that you can see here, in order to foster the integration of storage in the system. Okay. Now let's have a look on the two pilot projects led by Terna. So we have the power intensive and the energy intensive. I will focus on the power intensive, but I just will give a brief introduction also on the energy intensive project. So this project was developed to test the capabilities of ESS to reduce the wind energy curtailment. So 3 sites in the south of Italy were realized for a total amount of 35 megawatt with a technology, a battery technology named NAS, so sodium sulfur batteries, which have a huge capacity of storage. So they can store a big amount of energy that is, let's say, good for this kind of application. As for the storage lab, as also we can understand from the name, this is a laboratory where there are several battery technologies installed. There are lithium-ion, Zebra, flow batteries, and others. And let's say the objective of this project is to assess the ESS capability in providing ancillary services to the grid. Storage Lab is based in 2 HV stations in 2 main Italian islands, in Sardinia and Sicily, for an overall capacity of 14 megawatt. Okay, here you can see the complete portfolio of the ESS technology that Terna is testing. On the top of the slide, there is the rated discharge time for each technology, so ranging from energy intensive ESS on the right to more power intensive solution on the left. In gray, we have the technologies that are already installed and in exercise, while in green, we have the ongoing activities. So as for the technologies, we have as we said, in the energy intensive project, we have the NAS batteries. After that, we have the vanadium flow batteries installed in the storage lab, where let's say the main feature is that power and energy is decoupled. Then we have the Zebra battery, or sodium nickel chloride battery. After that, we have 6 kinds of lithium-ion battery, where each one is characterized by a different cathode chemistry. And after that, we have an ACDL, so an electrochemical double layer capacitor, designed for more, let's say, power intensive application. In green, as I told you, you can see the ongoing activities. So we are planning to install a flywheel energy storage system, and the virtual storage plant is an innovative control system that will allow Terna to optimize the operation of such plant. Okay, so when Terna started the Storage Lab project, we defined a double approach for the testing of ESS. There was a first level of testing led in cooperation with the main Italian laboratories in order to run tests at a module scale. And in parallel, we made tests at grid scale in the plant installed in Sicily and Sardinia. Some of the tests run at module scale level were made to evaluate the aging of the modules, their performance, and also the behavior in case of failure, for example, in case of short circuit. or in extreme operation, or for example, overcharge and over-discharge test. On the other hand, the testing at grid scale had the objective to verify the capabilities of ESS in providing ancillary services, for example, primary and secondary frequency regulation, voltage regulation, and so on, and also to evaluate and also monitor the capability of ESS in terms of efficiency and energy capacity during the years of the testing. So the target of this double approach was not only to assess the ESS capability to support the power grid, but also to compare different technologies and identify which technology suits better each application. Okay, let's briefly focus on the module scale test. Four main tests were carried out. The thermal and electric modeling were made in order to define a model for each technology and build an equivalent circuit model also useful for simulation and studies. Then we have the failure behavior test that aimed to assess the behavior of modules in case of extreme operation, and that gave us also useful information for safety. Then we have the test for the behavior in non-standard condition, which means testing how the performance of ESS can vary in different, for example, thermal operating condition. And after that, maybe let's say the most interesting is the aging test that aimed to study the way in which the aging of modules is dependent on the exercise condition, and especially on the characteristics of the cycles, of the charge and discharge cycles. And so, for example, the power profile, the number of power inversion, and so on. So Terna defined three kinds of cycles to carry out the test. We have the standard cycle, which basically is the cycle defined by the battery manufacturer. Then there is the frequency regulation test that mimic the ancillary service of primary frequency regulation. So we have a lot of power inversion, even if there is a low energy exchange with the grid. And finally, there is the current steps test, which is more stressful than the frequency regulation in terms of energy output. So let's see some results from the aging test, because they give some evidence about a tricky topic that is the one of the battery aging. So here we can compare the behavior of two different lithium-ion ESS named SDA5 and SDA6 after the aging test carried out for standard cycle and frequency regulation cycle. The comparison is made by assessing the residual energy capacity in percentage of the rated one, so the beginning of life, the capacity at the beginning of life, in respect to the number of equivalent cycles run. So as expected, we can see that the frequency regulation cycles are more stressful for both ESS, even if we can see that for SDA5, there is a small difference in terms of reduction of energy capacity, while this difference is bigger for SDA6. So it means that SDA6 has been more degraded by the frequency regulation cycle. So we can conclude that, for example, SDA5, the lithium technology of SDA5 is better for fast frequency application than SDA6. Moving to the efficiency test, here we have some interesting results by comparing the efficiency at grid and module level and the efficiency in different operating conditions. So on the left, we compare the efficiency at module scale level, so in green, with the efficiency at grid scale level in gray for different technologies, lithium, Zebra, and NAS battery. Obviously, the efficiency at the grid scale is lower for every technologies because it takes into account also the losses due to power converter, transformer, and auxiliaries. And in particular, I want to highlight that for Zebra and NAS battery, the consumption of the auxiliaries is even higher than the lithium one, because these are hot temperature batteries, and so they must be kept at a certain high temperature in the order of 300 Celsius degree in order to operate. So their round trip efficiency is low. On the right, we can see how the efficiency is impacted by the rate of utilization of the ESS. For example, in the case an ESS is operated just to provide the one service of primary frequency regulation, the efficiency is pretty low, between 15 and 30%. While if we add another service as the secondary frequency regulation, the efficiency is higher and close to nominal value, and so between 65 and 80%. And this behavior is common also to Zebra technology. So this is because primary frequency response, as we already said, requires an high number of power inversion, but has a low energy content, this kind of cycle. So if you consider that the losses of the auxiliaries could be considered more or less constant, obviously if the energy exchange is low, also the efficiency is very low. So it's better to operate the batteries in condition, let's say, similar to the energy exchange that we have in standard cycle, and this could be made also by combining different grid services. Indeed, in the ESS installed in the storage lab are capable of providing, as we told, different grid services. And Terna can control and also configure the features of these services remotely. So the ancillary services can be provided one by one or simultaneously, and always respecting the limits of the ESS in terms, for example, of available capacity. So in order to properly control the ESS, Terna Define can obviously activate or deactivate function according to the grid status, and also Terna can assign a priority index 1 to 4 to each function in order to manage the ESS, for example, for active or reactive power priority. And as we can see from this picture, let's say the different set point of power required by each dispatching function is combined in order to define the red profile, which is the actual power profile. Finally, I want just to show the results from a test made at grid scale level, which is the test of power inversion. This test has the objective to validate the fast response, the capability of fast response of ESS. Here on the right, we can see the results of one of these tests made on one of the ESS installed in the storage lab. In red, there is the trigger for a power request, while in blue we have the power provided. So the picture shows that the ESS is capable of power flow inversion within 100 milliseconds, additionally providing the maximum of isoverload power. So it goes from the nominal power in charge to 130% of nominal power in discharge. This is possible because all the ESS in storage lab are designed to have an overload power capability between 10 and 30% of the rated power. So thanks to this feature of ESS, we can conclude that ESS are, let's say, can be considered relevant resources for fast services. For example, the contribution to defense plan or to fast frequency services. Okay, now finally, just some hint about the ongoing activities in the storage lab. The first one is named Virtual Storage Plant, or VSP. And this is an innovative control system that allow Terna to control and operate the ESS installed in the storage lab as an equivalent storage system named UAE. This is made thanks to this VSP control system that has a virtualization and optimization function. Thus, the virtualization allow to the aggregation of the single ESS in one equivalent UAE, while the optimization consists in an algorithm which allows Terna to operate the equivalent ESS by trying to minimize a cost function that in this case is based on minimized ESS aging. Then VSP has also other 3 modules. The first one of the control and switching that just permit the control of the single ESS. The module of advanced monitoring that enhance the controllability and the observability of the status of the ESS. And the testing unit, which allow to implement some automatic procedure for advanced characterization test. And finally, the other activity ongoing in storage lab is about the installation of an energy storage system based on flywheel. This system is completely different from the technologies already installed, which are stationary storage. In this case, the flywheel system is an electrochemical energy storage system, which store electrical energy as kinetic energy of a rotating mass with a big mechanical inertia. So the flywheel energy storage system is designed for ultra power intensive services, and indeed the size in terms of energy is very low. And at the moment we have completed the testing on a small scale prototypal flywheel in order to validate the mechanical design and the control algorithm. Okay, so finally, in conclusion, we can see that in the next almost 10 years of experience, Terna has developed a huge know-how on all the phases of the ESS project, from the procurement to the specification and operation. And this experience allowed Terna to define the rules to properly open the market to ESS, as we have seen in the first slide. Okay, so I've finished, and thank you for the attention.
Thank you very much, Domenica. Very interesting presentation. I'll pause just 5 minutes here for questions to see if anybody has any questions for Domenica. Please raise your hand or feel free to send them using the questions box, and I'll be happy to read your questions on your behalf. So quick questions from Hydro Ottawa, Canada. Do you plan on testing solid state or vanadium batteries?
Okay, the storage lab, since is an activity authorized by the Italian Energy Authority, we have a fixed size for this project, which is 16 megawatt. And with the flywheel system, let's say we reached this limit. So we, as TSO, we are not allowed to install other technology. So unfortunately, we won't test this kind of battery.
Thank you, Domenica. Any other questions from the attendees today or panelists? Okay, we will still have time for the general Q&A session. Should you have any questions, feel free to ask them then. For now, we'll move on to the next presenter, who is Belén Segura from Red Eléctrica of Spain. She is working within the electric planning department, and she has more than 20 years of experience working for them. In 2010, she joined the electric planning department, where she has been involved in the national planning process. She also participates in different international groups under ENSO framework, where she's mainly focused in the development of a 10-year network development plan. So Belén, thank you very much for joining us today and agreeing to present to our utility members and guests. I will hand control over to you, and we can start with your presentation.
Okay. Good afternoon, everyone. Thank you for inviting us to this workshop. Let me show you my screen. Let's see if you can look at it. It's okay for you? Can you?
Yeah,
okay.
yeah, it's perfect.
Okay. Yeah, my name is Belén Segura, yeah, and I work for Red Eléctrica de España, the Spanish TSO, in the electrical planning department. So today we are going to talk about the role of the battery storage as fully integrated network component, mainly. So let's start then. Let's see. Okay. So the energy transition implies a substantial change never before experienced in the electricity system, characterized fundamentally by a significant growth of renewable generation to make possible the decarbonization objectives set both in the European environment and as well as the national level in the National Energy and Climate Plan. This National Climate Plan was delivered by the Spanish government to the European Commission in March 2020 and finally approved in April 2021. So according to this National Energy Climate Plan, the renewable energies in Spain, mainly wind and solar photovoltaic, will cover around 74% of the national annual electricity demand in 2030. So this new scenario summarizes to all the uncertainties linked to the current development of promising technologies associated to storage, generation, and transmission. And for that, it means that translates into a whole set of challenges and opportunities for the electricity system operator. So, what are the main challenges for the operability of the electricity system in the next decade? So first one, we can talk about that in the future, renewable energy production, such as wind and sun, whose energy cannot be stored, will play the main role. So well, currently in the Iberian Peninsula, the required balance between generation and demand is obtained through interconnections, storage mainly hydraulic, demand-side management, and so on. But on the islands, on the Spanish islands, without interconnections, this balance is even more difficult to achieve. So in the future, the electricity system will have to rely on more flexible resources, efficiently adapted to energy production based on non-storable renewable resources and the new consumption patterns of increasing electrified sectors. So the question would be, what does the system need in order to ensure the electric power supply balance as well as the safe and efficient integration of renewable energies? Let's see afterwards. So the second challenge has to do with the centralized production, self-consumption, storage, and the active consumer that will introduce new key factors into the system. In this way, distribution networks will become two-way networks which, apart from feeding consumption, will deliver energy to the transmission grid. Nevertheless, the transmission grid will continue be the backbone of the electricity system, as it will allow for the movement of large quantities of renewable energy from areas in which production is greater than consumption to other areas where production is not enough to cover demand. So here the question is, how will the role of these new issues be combined with the existing ones? And the third challenge has to do with the fact that renewable production is not connected synchronously, but with power electronics. And that means changes in the system properties and behavior. So how do we ensure the stability of the increasingly electronic power grid? So to answer these questions, to predict and answer appropriately these questions, the Spanish system operator, Red Eléctrica, has carried out a set of studies. So, as already said, yeah, Red Eléctrica has carried out this study that complements those already that has been performed in the framework of the Spanish electricity network planning process that covers horizon from 2021 to 2026. This new set of studies is well, try to aim at identifying and as far as possible anticipating the challenges and needs for the safe operation of the system in the future medium and long-term scenarios, and evaluate the technical feasibility of the future operation of the system. The studies performed are based on the 2026 scenarios used in the electricity network planning process ongoing, and also are based on the 2030 horizon based on the National Energy Climate Plan. So although these studies covers the Spanish peninsular system and the isolated islands, Balearic and Canary Islands, here in today's presentation we are only focused with the isolated systems, Balearic and Canary Islands. These studies performed cover various fundamental aspects from the perspective of the system operations. So first kind of studies are the one that are called generation balance, that means annual simulations of hourly unit commitment and economic dispatch. And as a result, we obtain the annual penetration of renewables, CO2 emissions, curtail renewable energy sources, and so on. From the result of these generation balance studies, from these economic dispatch studies, we developed another kind of studies to assess the flexibility needs. And finally, additionally, the frequency stability has been also evaluated. These studies are focused on the capacity of the system to maintain the frequency within the admissible limits in the event of possible generation demand imbalance incidents. So let's start to talk about the results about the Balearic electrical system. So in the Balearic Islands, the strategy to get the decarbonization of this electricity system is based on the reinforcement of the interconnection between the Iberian Peninsula and Balearic Islands. So nowadays, the Balearic Islands are connected with the peninsula through an existing HVDC, and the reinforcement we are proposing consists of an installation of a second HVDC of 400 megawatts capacity, and as well as a set of batteries of 140 megawatts and synchronous condensers. So the new HVDC link will increase, of course, the interconnection capacity between this system, the islands and the Iberian Peninsula, and therefore, of course, continental Europe synchronous system. So at the end, the Balearic island system will take advantage of the greater penetration of renewable energy that can be managed in such a large system. The batteries are defined as fully integrated devices in the system and will allow a higher level use of the existing HVDC between the Balearic system and the new one, and also of the undersea cables between the three islands. So as you can see from the figure, there are Mallorca Island is connected through Menorca through an AC subsea link, and at the same time, Mallorca is connected with Ibiza and Formentera system through also a double AC link. So from the figure, from this figure on the left and at the bottom of the slide, we can see that by 2026, balance results show a great coverage on the demand in the system coming from the Iberian Peninsula. You can see the difference. This orange part are the energy covered by the HVDC links. And here you can see that this energy coming from one HVDC is much lower. So it can be concluded that the whole reinforcement package of the interconnection between the peninsula and the Balearic Islands, that means the HVDC, the batteries, and the synchronous condensers, planned for 2026 will make possible to more than double the energy transmitted from the peninsula to the Balearic system and increase exchanges by 35% and 37% between Mallorca and Menorca and Mallorca and Ibiza respectively. Considering this reinforcement in 2026, CO2 emissions will be reduced by 76% in 2026, and the variable cost of generations in the Balearic Islands could be reduced by 80%. So finally, we can state that the proposed reinforcement allows to achieve a share of demand from renewables of 73% and a reduction of 85% in fossil fuel production. So, what about flexibility and frequency stability studies? Well, the installed renewable energy source capacity will be doubled by 2026 respect to today's values. So the production from solar photovoltaic on demand will reach values of 25% by 2026 and 35% of the demand by 2030. So looking at the figure, these figures in the middle, the one in the one here in the up place of the slide represent the reserve profile in 2019, and the one in the bottom represent the reserve profile in 2026. So the commissioning of the second Peninsula Balearic HVDC link, together with the batteries and the associated synchronous compensators, offers the system the entire reserve to ramp up in emergency situation to cover the failure of an HVDC pole or an AC undersea link between islands. That means that batteries as fully integrated elements can only provide these ramp-up reserves in this N-1 or failure situation of one of the links, HVDC or AC links. So the foreseen increase of renewable capacity in this system from other side means, as you can see in this figure, means a very high decrease of system inertia. So in both cases, it means power electronics coming from HVDC or coming from renewable energy displaces synchronous generators, and thus the inertia of the system decreases. So to compensate for the loss of inertia and lower short circuit power, the installation of synchronous compensators are proposed or is required in this system in order to ensure the correct operation of the HVDC links. So at the end, the stability of the frequency is supported by the emergency control of the Peninsula Balearic Islands links and batteries. These batteries, as fully integrated elements, are only activated in a standby situation and are only activated when there is an HVDC pole trip or an island AC interconnector trip. Let's see the case of the Canary Islands. So the strategy to decarbonize this system is totally different, or it differs from the one we have defined in the previous slide, and aims mainly to get the needed flexibility and system strength to allow the maximum renewable energy sources penetration. Well, as you may know, Canary Islands are not connected with Iberian Peninsula. There are several existing AC subsea cables between some of the systems and some planned for the future, but there is no connection with a big electrical system as Iberian Peninsula. So the objective of increasing renewable integration is achieved by means of course, linking islands with undersea cables. That is the case of Gran Canaria, that is here, with the system of Lanzarote-Fuerteventura. This is a future subsea cable, and of course, also this objective is commissioned by the installation of storage, hydro pump and batteries to provide system inertia and reserve needed to cope with imbalances. So in the Gran Canaria Lanzarote Fuerteventura system, it is essential to have a storage that allow the integration of existing and planned renewable generation, in addition to collaborating in its balance and frequency stability. In the 2030 horizon, the pump storage generation allows maximizing the benefit of the system of the Gran Canaria Lanzarote Fuerteventura system interconnection by increasing the share of renewable generation from 37% to 48%. If we consider the other system, Tenerife-La Gomera system, in the 2030 horizon, the battery system is not enough to increase the share of renewable generation and needs to be complemented with a system with greater storage capacity, such as hydro pumping, as in this system. So, looking at national climate energy plan, it establishes for the Canary Islands a target of 58% of renewable energy integration. Considering considering hydro pumping and batteries in the system, we are, even though we are not able to reach such target, we are reaching only, we are reaching 45% of renewable energy integration. That means that we should continue studying and new technologies in order to be able to integrate more renewable energy in the Canary Islands. So regarding flexibility study, maybe for you to have an idea, by 2030, we expect to have 1,700 megawatts of wind energy in the Canary Islands and around 500 megawatts of solar photovoltaic. For you to have an idea, the peak demand of the Canary Islands is around 1,700. So for sure there will be hours in the year where renewable energy production will be much higher than demand. So considering the variable nature of the renewable energy source of wind and solar, system flexibility, of course, is needed to integrate the greatest amount of them, and at the same time minimizing curtailment and always keeping system security of supply. This primary resource variability obliges the rest of the system to accommodate and evolve in order to make room for renewables in safe and efficient terms. Focusing on system development, this translates into interconnection capacity and increase and storage development. So the storage assets are essential because they significantly contribute to provide the needed flexibility to increase the possible amount of penetration of renewable energy over demand and minimize this risk curtailment. Well, as it can be seen in these figures, in the bottom figures, the renewable production over demand that the system will be able to cope with in safe terms, that are the blue points, this part. This is without storage, and this is on the left is without the storage, and on the right with the storage. So these blue points that represents the renewable production over demand will increase from around 65% to 85% when hydro pumping is considered in 2030. So that means we have here these blue points that will be higher if we consider hydro and batteries itself. So furthermore, the curtailment that it is represented by the green points here will not be significant until renewable production over demand is higher than 75%. So if pumped storage is not considered in 2030 scenario, curtailment will be noticeable for renewable production over demand higher than 50%. That means that this curve, this green curve, are placed to the left so that when storage are considered, and that means curtailment is higher levels of curtailment are avoided. Regarding frequency stability studies in the Canary Islands, we can see that the foreseen increase of renewable capacity in these isolated systems means a great, again, decrease of system inertia, as we have explained for Balearic Islands as well. So power electronics, again, that are coming from renewable energy sources, displaces synchronous generators, and thus the inertia of the system decreases, as it is expected. So the energy transition in this system is not possible without the development of storage, and of course accompanied by the increase of installed power. So the increase of renewable energy capacity is worsening frequency stability by the increased probability of operation demand imbalance occurrence. And finally, through these studies, there have been found that additional needs for primary reserve and fast power frequency regulation through batteries, advanced renewable controls, and so on will be needed. So finally, just I would like to give you some conclusions for the study we have presented. First one is that the high share of renewables in these isolated systems foreseen in the electricity system of Balearic and Canary Islands poses, of course, a great challenge from the point of view of a secure and efficient operation. Storage systems, together, of course, with interconnections and networks in general, but storage are one of the key elements for the renewables integration and the security of operation, because they will provide reserve, fast power frequency regulation, and avoid rest curtailment. The role of the storage systems today is especially relevant in isolated electrical systems, and the technical and economic justification arises much earlier than in interconnected systems. That's why we have presented here the results from these systems. Main approach for the decarbonization of the Balearic system is to reinforce the interconnection capacity with Iberian Peninsula through a second HVDC link, as we have explained, and plus very important, fully integrated batteries that maximize the capacity of these HVDCs, as well as the AC links between islands. For the Canary Islands, the strategy is different, but storage and AC island interconnection has been identified as key enabler of balance and system operability, providing the needed system flexibility and strength to maximize rest penetration. Last, we would like to say that these studies, the system perspective analysis, provide the transmission system operators with a valuable tool to identify and get ready for the operational challenges arising in future scenarios in order to be key enablers for the energy transition. Well, that's all from my side. Thank you for attending my presentation.
Belen, that was an excellent presentation. Thank you so much for sharing perspective from Red Electrica with our predominantly North American-based utilities. I'd like to take 5 minutes for Q&A quickly to see if anybody has a questions. Feel free to raise your hand. I will start with some written questions, and Belen, if you expand the questions tab, you could see that I assigned some of the questions to you, just so that you can read them while I read them as well.
Okay.
So the first one is from Right from Hydro Ottawa. He's asking, how was this plan hatched, and what did it take to get it approved, and in what time frame?
The plan, sorry, I cannot see the question because let's see.
It's okay, I can just read it for you.
Okay. Okay, well, can you read it again, because I cannot hear,
Sure,
I didn't hear you, sorry.
No problem. So the plan that Red Electrica put in place for the battery energy storage, what did it take to get it approved, and what was the time frame?
Okay, well, this plan, well, these studies have been done complementary with the national planning studies that are currently ongoing, and it covers 2021 from 2021 to 2026 horizon. So but this national plan is not approved yet, is ongoing, and we expect having well, not very late having this plan approved with well, this information about batteries and storage plan for these isolated islands included.
Okay, thank you, Belen. Next question is from Richard. Are biofuels, along with solar and wind, considered in achieving renewable goals for the island?
No, no, not for the moment. Only the national this national climate energy plan only consider for the islands, or at least for the moment, solar and wind, to replace fossil fuels, very expensive fossil fuels generation in these islands. Well, in Canary Islands, these solar and wind renewable sources are very high, and the foreseen capacity, future capacity, is quite high. Not is in Balearic Islands, it's not the same. It is expected to have an increase in renewable energy, but not as high as in the Canary Islands. So in the Balearic Islands, we have this HVDC connection, and the strategy is to more goes to cover Balearic demand with Iberian Peninsula energy.
Thank you, Belen. Another question from Kieran from Certain Company. What duration of energy storage system do you see will be required for the Canary Islands?
What duration?
Yeah, so duration, I guess, like long storage duration in terms of how long can this energy storage can excuse me, supply the energy for Canary Islands, and for what purposes? And Kieran, if you'd like to elaborate more, let me know by raising your hand and I'll unmute you.
Well, I don't know if I understood properly, but the storage power plants planned in the Canary Islands are needed in order to integrate renewable energy in a safe and secure way. We are expecting to have a huge increase of these sources in this isolated system, and on the contrary, for Balearic Islands, they are not connected with a higher system. So there are a lot of hours. If all the renewable energy is expected are installed, there will be a lot of hours with higher curtailments coming from renewable energy. So at the end, this renewable energy integration could only be possible with the installation of this storage, that is a combination of hydro pumps and batteries, because batteries itself, alone itself, cannot provide a high level of RES integration.
Thank you. Two last quick questions before we move on to the next presenter. Kieran, go ahead.
Yes, are you expecting multi-day storage to be required for the Canary Islands, or do you think that they can do with a battery, say that's 8 hours?
I think, well, yeah, test will be needed. This is quite new. We have just started making these studies, and yeah, we will need more studies to define exactly the operation of these batteries and storage in the Canary Islands system.
Okay, thank you, Kieran. A question from Flavia from ONS Brazil. Have you used batteries for fast frequency response to replace inertia in Spain, and what is the response time for such application?
Well, in the batteries that are defined in the Balearic Islands are defined as fully integrated elements and cannot provide such service only. Well, can provide such service only in the in case of HVDC pole failure on an AC link failure. It cannot provide. We know that we know that the batteries. Or at least it is we have been said that batteries can provide inertia, but the main function as fully integrated elements in the grid, not to modify generation market, is to provide this service only in a link failure situation. So not for the moment as a fully integrated element in the system.
Okay, well, Belen, thank you so much for the presentation and answering some of the questions from our members. We will move on to the next presenter in line, who is Bobby Smith. Bobby Smith is the head of energy storage in Ireland, short for ESI. He's a representative, the ESI is a representative body for the energy storage industry in Ireland. Bobby works with ESI members and policymakers to promote the development of energy storage on the island and remove barriers to the integration of new flexible technologies. Previously, Bobby worked as an analyst in the Commission of Regulation of Utilities, where he was involved in areas such as electricity network policies, security of supply, and the development of the DX3 system services market arrangements. So Bobby, welcome on board. Thank you for supporting us with this event and agreeing to present to our members. I'll hand control over to you in just a second here. And it will be a good opportunity to unmute.
Yes, thank you very much for the introduction. I'm just going to share my screen 1 second.
Yeah, we hear you.
Okay. Is it possible to almost decide which screen I'm sharing? It doesn't give me an option.
I can give you feedback. Before you were sharing the browser, so maybe you want to show the other screen.
Fair enough. Okay, there's 2 screens. So you see that now?
Yeah, that's perfect. Just full screen
Grand,
mode.
there we go.
There you go.
Yep. Okay, thank you very much. Sorry about that. So thank you for the introduction. Yeah, so I think you've given kind of what we are as ESI and who I am. So I might move on to that. Just very briefly, just to reiterate, we are a representative body for the energy storage industry in Ireland and Northern Ireland. We have over 39 members from across the energy storage supply chain. And generally as an association and as a policy team, we're working to facilitate the deployment of energy storage on the island and help meet our decarbonisation goals. So just a bit of context on the Irish power system for if people aren't aware. So it's a synchronous island power system, very lightly interconnected with Great Britain via HVDC links. Ireland has a large amount of installed wind capacity relative to demand. So Ireland has a really strong wind energy resource. We achieved 40% RESI in 2020, mostly from wind generation, and our government has set a target of 80% RESI for 2030 and ultimately net zero by 2050. So the kind of challenges for Ireland in terms of the location of generation and going forward meeting higher RESI targets is that large amounts of wind generation are typically located in remote areas in the west of the country, whereas the majority of demand is in the east. So the whole power system is designed to get large amounts of wind generation from the west to the east of the country. As well as that, large volumes of offshore wind are are in development that are due to come online in 2030, which is basically on the east, south, and southwest coasts where those projects will be located. So in terms of the kind of issues we see and why energy storage and battery storage in particular is so important for Ireland at the moment is that Ireland has a very constrained grid and system security limitations, which minimize the amount of available wind energy we can use on a daily basis. So I think just it's important to kind of clarify, I think at the start, what we mean when we talk about dispatch down in Ireland, because it does differ to the continent in Europe when they describe curtailment and constraint and those issues that they see. Ireland has slightly different issues, perhaps as a synchronous power system, island power system. It's seeing issues now that the continental power system will start to see in the next decade or more. But right now, our TSO EirGrid has to manage system security, and to do that, they must keep a certain amount of conventional, typically fossil fuel generators, running on the system at any one time to provide system stability services such as inertia, voltage, or fast-acting reserves. This means that the total amount of wind generation that can be dispatched in the system relative to demand at any one time is 75%. So anything above 75% in terms of demand that can be met by wind generation has to be turned down, and that's called curtailment. And that's a system-wide issue. So if we have a very windy day in Ireland and that 75% limit is being breached, TSOs will proportionally turn down wind farms to make sure that 75% limit is respected. And then as well as that, we also have local network issues in terms of constraints, in terms of getting bottlenecks in the grid, congestion on the grid, power transfers from west to east. Those are local. So wind farms that are impacted by constraints are dispatched down due to constraint issues. So storage as a solution can help in both curtailment and constraint. And I'll kind of get into a bit more detail on that, how it's going to contribute there. Just one other thing as well, there is at least in theory, another form of dispatch down, which is oversupply. So on a system like Ireland's with large amounts of installed wind generation in future, there will be times where demand is just simply not going to be high enough to meet that level of wind generation, so excess generation will be turned down. That's not an issue at the moment so much, but it will become more of a prominent issue by 2030, and that's typically where the longer duration types of storage we see fitting in there and being a solution. But just to jump on, in terms of this dispatch down of wind generation, the blue kind of columns on this chart show the installed wind capacity in Ireland year on year. And you can see in 2020 is roughly over 5 to 5.5 gigawatts of installed wind generation. That's compared to a typical peak demand, which is around 5 to 6 gigawatts. So a lot of wind generation relative to demand. The red line there in the graph shows the overall dispatch down amount year on year, and you can see that there's been a pretty steady trend of that increasing year on year. Roughly that 13% of wind generation, which was dispatched down in 2020, that's around a 50-50 split between curtailment, the system-wide security limitations, and constraints, so the local network issues. But we are seeing the constraints becoming more and more of an issue as they're building more wind onto a system, and the grid is struggling to keep up and accommodate it. Something I thought might be interesting, as we do a survey of our members each year to understand the amount of storage projects in development, typically battery storage, and we try to quantify that in this slide here. So overall, based on our survey last year, there's just under 2,400 megawatts of battery storage in development on the island. The majority of this is, in terms of planning, that's the consenting and permitting phases. The majority of that is actually through the planning system or in the planning system at the moment. And then there are other projects with grid offers from our TSOs, and then a defined route to market, which we define here as essentially in construction. So on the right there, there's 356 megawatts of battery storage that's already operational in Ireland, and that route to market, 467 megawatts, is in active construction and will due to become online in the next year to 2 years. So there's quite a lot of battery storage on the system already, and a lot more to come online in the next 12 to 18 months. What is kind of driving this battery storage build out is a framework called DS3 System Services, or ancillary services, they're known as in other countries. So primarily this is our TSO is procuring fast acting reserves to manage system frequency. And these reserves are mandated to respond in milliseconds to system events, to responses to frequency triggers, such as the sudden unforecasted trip of a conventional unit or an interconnector. And we've carried out a study with Bring Consultants, which we published just over in late 2019, which looked at the ability of providers such as battery storage, synchronous condensers, even renewables, etc., to provide these types of ancillary services and replace the need to constrain on or dispatch fossil fuel generators to provide them, and thus alleviating our curtailment issues on the system. So what this is doing is effectively allowing more space on the system for wind generation, because the TSOs don't have to constrain on or constrain up or down a fossil fuel generator to provide the likes of inertia or fast-acting reserves. So quantifying this in a study, Baringa modeled the 2030 power system with essentially all these system services being provided by low carbon, zero carbon providers, so non-energy providers like battery storage, synchronous condensers. And the results show that we could save 2 million tons of CO2 per year because we don't have to dispatch on and run conventional units as much. We could save 117 million per year. That's through avoided operational costs from these conventional units through fuel and carbon costs. And we can also reduce renewable curtailment by 50%. Essentially, we'd be able to increase that 75% limit at the moment on synchronous renewable generation. We could increase that up to 100% by getting all these services from non-conventional sources. So in terms of the battery storage build out, that's been really successful so far in delivering the amount of reserves that we would need to do this. The defined kind of requirement for reserve in Ireland is based on the largest single infeed, which is typically an interconnector of 500 megawatts, and further interconnection is in development. So our let's say our largest single infeed loss would be around 700 megawatts in future. Therefore, there needs to be a more or less equivalent reserve requirement to match that that particular loss, which battery storage is well geared up to do so in Ireland. Just a bit more on that DS3 system services framework. So just how it works. It was established in 2017, essentially for our TSO ERGO to procure system services from market participants. There are 12 services, but they're commonly grouped in kind of blocks of inertia, reserves, voltage, and ramping. And as I said, these services are needed by the TSOs at all time to maintain system stability. So they'll always be almost continuously ensuring that these services are available on the system and dispatching units accordingly. The way units can provide these services and get contracts is that there's a gate framework that opens every 6 months for providers. If they've built and they can go through a testing process and prove they can provide the relevant services, they'll essentially receive a contract for those services and the level of provision they can give. Each service has a tariff rate associated with it, and providers are paid per megawatt of availability for each service. So it's not a competition. Providers aren't setting the price, it's the TSO setting the price, and then the providers come in and prove they can provide the service and get that price. There are also things that kind of bonuses, let's say, called scalers, that incentivize certain performance, so faster speed of response, enhanced reliability, things like that. What is managing the spend in this, though, is that the TSOs have a budget of 235 million per year, which is set by our energy regulator to spend on system services. And also a bit of a handicap on this is that the current framework, which batteries are delivering under to secure these contracts, is due to end in April 2024. So as an industry, we're unsure what comes after that, and there are plans in place to develop a new framework, but there's no clarity on exactly what that is. This is just for interest. I thought just show a couple of the battery projects that have developed in Ireland so far. So that 356 megawatts, that's made up of around 10 projects. They vary in scale, some up to 100 megawatts, some as low as 10 megawatts. Typically shorter duration projects, I should say, because the fast frequency services typically require energy out to 20 or 30 minutes. So a lot of these batteries are typically half-hour in duration that are primarily geared up to provide millisecond responses to frequency events. This is basically the build-out graph we have from a survey of our members. So we predict by October this year, there'll be around 700 megawatts of battery storage contracted and providing a fast-acting reserve on the system. Again, primarily short-duration half-hour batteries. There is issues with the existing budget for system services in terms of that spend, and that budget is becoming a bit overheated. So I expect that the cap has essentially been reached on shorter duration batteries in Ireland, and where the market goes from here is now the kind of next phase of evolution that we're very keen on advancing. And that's typically a move to multi-hour projects and even longer duration emerging energy storage technologies. And just to touch on that piece then, so we're actually carrying out a study at the moment, again, with Baringa to almost try and address that question. Now that the market has essentially delivered a lot of the fast-acting reserves via batteries that can essentially reduce the amount of fossil fuel generation running, what is the next phase of the evolution of the storage market towards multi-hour projects, or even daily storage in terms of duration capabilities. So we've contracted Bringa to carry out a study. I'll be able to present some of the provisional results here, but the study is ongoing. So these may be subject to change, even though I don't think they will be in reality in the final publication, and that'll be available on our website in the next few weeks. But essentially what we wanted Bringa to do is analyze the system-wide benefits of different portfolios of energy storage, and also the local network benefits by modeling storage behind certain constrained regions of the Irish network. So what they've done is they've assumed that the battery storage build-out of half-hour batteries peaks at 700 megawatts in all scenarios, and they've modeled the 2030 power system with different portfolios of 2 gigawatts each of different durations of energy storage. And they also have a very duration scenario on the right there, where they've modeled almost a mix of everything in terms of the duration of projects. So this is anything, as you can see, from 2 hours up to 100 hours in terms of storage. And I'm going to show you kind of what impacts we've seen in terms of the benefits that has on the network. So the first one is on the emissions themselves. So we're modeling a 2030 power system with quite high RESI. So the emissions, overall power sector emissions, are already fairly low, but the kind of the leftover emissions in the power system are that much harder to remove, because you've already got most of the low-hanging fruit, so to speak, and then those last million tons of emissions are extremely difficult to remove, because you've almost maxed out the amount of renewable capacity you can deliver, and then it is just those hours with very low wind or solar output where you have to rely on other forms of generation, and that is the hardest to decarbonize, and that's where this energy storage, particularly the longer duration energy storage, does fit in. So you can see the different emissions reductions that the portfolios of storage have. So every storage portfolio is having some reduction in emissions, but the extra long duration, that 24-hour to 100-hour, has the most in terms of the emissions reductions. So that's obviously a signal that going forward for almost the post 2030 system, and that last 10 to 20% RESI, and those last million tons of CO2, is the long duration storage technologies that are really going to have to play a part. And how we bring that on the system is kind of a key question. Then in terms of the renewable oversupply, so this is the scenario where we have perhaps nearly 10 to 15 gigawatts of renewable generation on a system with a peak demand of around 6 to 7 gigawatts in 2030. So there will obviously be times when there will be oversupply of renewable generation, and the storage is going to play a particularly important part in that sort of balancing and that shifting of renewable generation via storage to hours where otherwise we'd be relying on fossil fuel generation, and essentially decarbonizing those fossil fuel generation hours. So the outcome of this is that, again, in the extra long duration scenario, storage can reduce renewable oversupply by 55% in both ROI and NI. That's a huge amount of renewable generation relative to demand in Ireland that could be decarbonised. And then just the second part of the analysis, we've also modelled an area of the network which is very constrained. It's in the northwest of the country. It's County Donegal. There's a lot of wind generation. It's a high wind resource county, but a very network constrained county in terms of the ability to get power out of the county via the transmission system to the rest of the country. So we've modelled essentially proportions of the energy storage in different portfolios, essentially in the Donegal region, to see what impact this has on the constraints of renewable generation. So what we've done is we've assumed a certain amount of wind generation in excess of what's in place today. So 440 megawatts of existing capacity, an additional 490 megawatts by 2030. We've assumed the T-1 methodology, which is how our TSOs operate the system. And we've assumed different portfolios again of storage duration, but just minimize them. So 200 megawatts in each scenario, as opposed to 2,000 megawatts for the system-wide scenario. So I think that probably the biggest impact of this, we have analysed other impacts, but I think that the biggest impact is on the actual constraints of renewables. So you can see in a base case with no storage and no new network build out, if we just simply added more renewable generation into Donegal, which and plenty of projects are in planning to build in Donegal still, renewable constraints would reach over around 30%. So 30% of the available wind generation would be essentially wasted because the network can't accommodate it. Storage, you can see, and of any duration, has a pretty significant impact on the level of constraints in terms of reducing them, with obviously the extra long duration scenario having the biggest benefit in terms of reducing constraints almost to zero. But even a medium duration, that'd be typically your batteries, 4 to 6 hours, reducing constraints by 10% by shifting that energy, whereas it would otherwise be lost. We are doing some analysis to kind of calculate what would that mean in terms of emissions, because obviously if this energy can't be used at a point in time, then some other generator is providing that energy, and that would typically be a fossil fuel generator. So right now that's part of the analysis we're trying to put into the final report, but that is a significant benefit, obviously for renewable generation in the area, obviously for decarbonisation overall in the system. And so this is a key kind of takeaway we want to bring from this report and try to get in place the systems that can incentivize this type of locational long duration storage, because right now we don't have locational pricing in Ireland, and we don't have specific locational incentives, network incentives to develop these types of solutions. So it's a very promising piece of work, we think. And then I suppose just to round up my presentation with just some I suppose conclusions and maybe questions we have going forward for the industry. I mentioned that we don't have locational pricing at the moment or locational signals. We also don't have long-term contracting framework specifically for long duration energy storage. So is that something that needs to be addressed on the system? We believe it is. That's where our policymakers can come into play. But it shouldn't prevent storage from stacking revenues across multiple streams. So that is one of the inherent benefits of energy storage, that it is flexible. It can provide multiple services, and we don't want to restrict markets in any way. There's a huge potential for storage to contribute to capacity adequacy, but our capacity market is typically designed for conventional assets, which I'm sure many people are probably familiar with in their own countries. We must recognize the system will be very different by 2030, and planning for net zero by 2050 must start now if we're going to achieve it. It does seem far off, but in terms of getting projects built, getting new technologies online, and alleviating network constraints, 2050 actually isn't all that far away. We believe the storage market will continue to evolve from half-hour duration projects more towards 1, 2, or 4 hour deployments in the near term, similar to what has happened in GB. We're already starting to see the first 2 and 4 hour battery storage projects in Ireland in development, due to come online in the next 2 or 3 years. Co-location with renewable projects will become more commonplace for sure. This is particularly in constrained areas of the network and maximizing the use of existing grid connections via hybrid projects. And then there is that long duration storage question. So that typically 10-hour plus, even 24-hour storage is what we've shown in our study is of huge benefit to the system in future. So it'll become an increasingly important policy priority, we believe, to establish a framework that can incentivize investment in those types of technologies. So I know that I've kind of gone through a lot of that pretty quickly, but happy to answer any questions, and just my contact details are there if anyone wants to contact me afterwards if any questions you don't get to today. So thank you very much.
Thanks so much, Bobby. Great presentation. I'm going to check the questions queue. So let's see. We have a question from Alessandro from Italy, Terna. He's asking, is there a centralized auction organized by the system operator to develop a new storage capacity in Ireland?
Yeah, so that's a good question. There is a centralized auction for capacity in Ireland, which is a technology neutral auction, at least in theory, where providers can compete for up to 10-year contracts to secure capacity at fixed payments. There are some disadvantages though for energy storage participating in that. So the TSOs assign reliability factors to different technologies, and storage is penalized quite a bit compared to other technologies. Even storage of longer duration is still penalized a bit. So there are auctions, and we do see some storage projects coming through there, but typically it's dominated by gas units and fossil fuel peaker plants.
Thanks, Bobby. A question from Kieran Sarton Company. Do you see green hydrogen or iron air batteries to fill the long duration storage gap in order to fully decarbonize?
Yeah, it's a good question. And the study which I just showed on the kind of longer duration stuff, we were purposely agnostic in that, in how we in what type of technologies we looked at. We didn't want to pick any winners, so we'd see really a portfolio of different energy storage technologies, whether it's hydrogen, iron ore, as you said, or different or other emerging energy storage types that could fill in that space. What we assumed in our study was a certain duration and a certain round trip efficiency. So I think the 24 to 100 hour, we were assuming something like a 65% round trip efficiency. And what we were doing is identifying the benefits, but not saying which technology would fit under there. We're identifying overall value, and any technology that can deliver within that value has a net benefit for the Irish system, and therefore that's the argument we're trying to make. But yeah, certainly I could see a multitude of technologies being active in that space.
Thank you, Bobby. A comment or questions from Ryan, Hydro Ottawa. Why are energy storage systems penalized?
Okay, is this what I just in the question in relation to the question I just answered before on the capacity market auctions? Yeah, so the capacity market auctions are designed to procure firm capacity, and to do that, the TSOs assign reliability weightings to each technology unit based on modeled experience of their ability to provide capacity at a point in time. So wind would have typically a low reliability factor because you can't dispatch it whenever you want for capacity if there's a system stress event. Storage, because it is energy limited, and because it's energy limited, essentially they assign a reliability factor as well, which would be lower than for instance, a gas peaking unit. So when you're competing for these contracts, you can only compete with you're competing with a kind of a weighting factor in place in the auction, which makes your project potentially less competitive against another. If that answers the question, feel free to send another comment if that hasn't.
Yeah, I think it has. Right, if you want to self-unmute, go for it. I'm just going to check some other questions here. Another question, has anyone considered tidal power and storage?
I haven't seen that on the radar here. Not in Ireland, no. But again, we're not closing the door to anything that comes through that can deliver within the overall. We're trying to demonstrate a value here, so anything that can deliver in that, it's fair game. But I have, at least in Ireland, I haven't seen that technology on the radar.
Thanks, Bobby. I have a question. Are there any projects or pilot projects to extend the end of useful life for battery energy storage in Ireland that you could share with us?
Sorry, what was the first part again? Just say that again.
Yeah. Just focusing on extending the lifespan or life cycle, end of useful life of battery energy storage. Do you have standards, maintenance practices, any interesting projects you could share with us?
Yeah, I wouldn't. Yeah, I don't have any projects at the moment. Everything in Ireland is relatively new, so we haven't addressed those types of questions yet. I would say for the purpose of the batteries that are in place in Ireland at the moment, the typically shorter duration frequency response batteries, they're not cycling often, so they have quite long life frames in terms of degradation of the batteries. But what comes after that is probably a question that I don't think we're addressing right now because it is an issue at the moment.
Well, thanks, Bobby. I think that's concluded the question to you. We do have a general Q&A session from now until 10:20 Eastern or 3:20 GMT. It's a good opportunity for a quick break, but before that, I just want to launch a quick poll here while we continue answering some of the questions. So please indicate your interest, your response, if you're interested to participate in an international survey to look at best practices and future plans for integrating grid-scale energy battery storage. Panelists, you cannot see the poll, but I'll be happy to send you the link and get your feedback if you haven't participated already. But as the poll goes in parallel, are there any questions for any of the presenters or just general comments, feel free. It's an interactive discussion. Just raise your hand, I'll unmute you and you'll be able to speak. Comments from John Saviston?
Yes. One very intriguing question, like after listening to all these presentations, there has to be an optimal ratio of installed storage on the system versus your renewable capacity on the system. Is anyone looking at what is that optimal ratio?
Do you want me to come in there? Yeah, I can try and answer that, and then
Go for it.
yeah, feel free to jump in on the other panelists. But yeah, it's sort of can be hard to identify, and that's what we're sort of trying to do with our study. You're trying to assume different capacities, and it is a bit finger in the air stuff in a way, because you only have a certain amount of scenarios you can run in terms of what's the most optimal capacity on the system. For instance, that 2 gigawatts figure we had, is that the optimal figure? Could it be more or lower? It's hard to identify unless you have a lot of modeling capability and a lot of money to do it. But I don't think, at least in the Ireland study, we're not identifying an optimal ratio, if that helps at all. Like, I suppose, just put it another way, you're probably looking at the amount of megawatt hours or terawatt hours in terms of a system that you would need to cover, let's say, your extreme events.
Yeah, there's all sorts of wishes and constraints here. Like it's a requirement to decarbonize your grid. It's a requirement to reduce fossil fuel use. It's a requirement to build out. But there has to be some sort of optimization algorithm somewhere, or has to be developed so that people can get guidance. If, for example, if you have 1,000 megawatts of renewable energy on the system, that could be a combination of wind and solar. How much battery energy storage do I need to optimize the use of that? And again, that would probably depend on what's your baseload generation. How much hydro do you have? How much of the hydro is run of the river? How much nuclear do you have? How much fossil fuel generation? So, like, to me, this is a huge question: how to optimize your grid, and how to determine how much battery energy storage do you need in your system to optimize it.
Yep, I'd agree.
Go ahead. Oh, sorry. Go ahead, Bobby. I'll refer to Kieran questions right after.
Yeah, no, I agree. It's not always easy, to be honest, to determine that, particularly with different generation portfolios in, wherever your region might be. In Ireland, it's slightly more straightforward because we don't have a lot of hydro, or we don't have any nuclear. So it is typically gas or wind meeting demand. So literally, you're just trying to balance that in terms of periods where it would be low wind and some solar in Ireland, but low solar output. And those typically, you're trying to almost ensure for full decarbonisation that you have enough capacity to meet extreme events, which would be extended periods, maybe week long, of a cold weather front with no wind, for instance, which does happen maybe once every whatever how many years. That's sort of the extreme scenario I think you have to plan the grid for, and then that's modelling, well, how much terawatt hours of storage is that, and trying to maybe come up with an approximation there for how much you might need. But that's it's maybe back of the envelope stuff, rather than me having the modeling answer right now for you.
Yeah, to me, this is the next thing that the policymakers are going to want to know. Well, how much do I need?
Yep.
Like, from what I've learned in the last 2 days from these presentations is that battery energy storage is an enabler to decarbonization of the grid, and an enabler to increasing the amount of renewable energy that can be on the grid. But then the next question is, well, how much do I need? And to me, this is the this will be an emphasis on research over the next year or two or three to come up with that number.
Yep.
I also agree. Yeah, this is not an easy task, but in our case, at least, we work with European targets. So to solve this optimization problem, we have the start point. Our start point is the European targets by 2030. That we are more or less obliged to have an amount of RES integration by 2030, and at the end goes to a zero CO2 emissions by 2050. So this is more or less our hypothesis, and with that also depends on the functionality of the battery, of course, but with that in mind, with that European targets in mind, we designed the size of the the storage batteries or whatever. But the profile of renewable energy is something given for us.
Thank you, Belen, for your comment. Kieran from Sarton, go ahead.
Yeah, I just want to make a comment there. Like, every region is different. Like in the southeastern United States, it depends on the percentage of penetration that you have onto the grid with renewables. So we're at 11% right now. I think Ireland is at 40%. So Ireland did a lot with very little battery storage because they had wind, but we have more solar. So we're not in the same situation. So, you know, when you talk about VRE penetration, it depends. What is your renewable source? Is it wind or is it solar? So, like, you know, I think what we're going to see is we're going to see more multi-day storage as grids go with higher penetrations, especially of solar. So, but a cheap 8-hour battery would solve a lot of problems for much of the utilities around the world for balancing and for energy shifting. But as we're trying to squeeze out that last bit of carbon out of the system, you're going to see longer durations. You may see 100-hour batteries, you know, or green hydrogen or something like that. But yeah, every utility is modeling that, and that's a big unknown, and it's going to depend on the region.
That's a good observation, Kieran. I want to mention that yesterday, the same question with respect to the ratio between energy storage and generation resources or renewable energy sources was mentioned, I believe, by Australia, that you would like to have 20 to 30% more generation than energy storage. Again, as Kieran said, that probably varies depending on the region and policies, but in terms of operation, that's a rule of thumb that has been recently used. Let's see if there's any other questions. I don't see any written questions. Any comments about some of the presentations from ICP Tech or from other speakers?
So if I can just interpret that rule of thumb properly, if you have, say, 1,200 megawatts of renewable on the system, you would need 1,000 megawatts of storage. Yeah. To me, that seems to be kind of high.
I guess it's a rule of thumb for meeting net zero carbon, like in 2030, 2040, and so forth, but I'm not sure. Right? Do you have any comment on that?
Yeah, I jump in. No, sorry, go ahead. Go ahead. Yeah.
Sorry, no, that's what was mentioned yesterday as a rough rule of thumb by providers of services. Mm-hmm. That it was 1.2 to 1.3 to 1 generation to battery. In projects that we did as a utility and we were involved in, I think the ratio we came up with was 3 to 1. So, and maybe one of the details is whether it's fast acting power type batteries or storage systems versus energy type storage systems. I don't know. But
Yeah.
it's a good question to still dig into.
Yeah, I was going to jump in as well. I think it maybe depends on the problem you're trying to solve. I mean, if it's the short-term balancing, then that's mainly batteries, and you could probably size that relative to the largest single in-feed potentially. And then if it's long duration, then you're trying to model, I'd imagine, scenarios in future where there might be a shortfall of generation. I mean, a shortfall of renewable generation if we're talking about full decarbonization, and that's what you're trying to model, the amount of storage hours you need to cover that. But then I think the other comment had a good comment as well, that it depends on also where you're getting your majority of your generation from, wind or solar, and will obviously determine how many hours of storage you need.
Can I just make a comment there? So for Southern Company, we're looking at carbon capture and natural gas as well. So, I think those rules of thumb, it depends on where you are. It depends on what your strategy is going to be going forward. The modeling that I've seen doesn't show that much amount of storage if you use carbon capture. So carbon capture might become a competitor to long duration storage because the versatility of natural gas, it's hard to beat that. And there are technologies out there that can do 90% carbon capture. And so depending on whether there's a carbon tax in the United States, that's something that we're looking at as well. So we're looking at the competitors to long duration storage as well as the different technologies.
Thanks, Kieran, for the comment. But as time goes by, would you say, guys, that the ratio is expected to increase, meaning that you will gradually need more energy storage as a ratio with respect to the generation resources, especially as it gets better, as it has faster response and more efficiency and cost? If the market is focusing on that as a way to improve system operations, you could see that in the future, 10 years from now or so, the ratio will increase. Is that a fair assumption to make?
Go first there. Yeah, I would say yes. And I'm speaking in the Irish context. I would say in general we would need some form of zero carbon energy or low carbon energy to provide to essentially balance the system at times when there are low wind or low solar periods. Now, energy storage, we believe, is obviously going to play a big role there. But I wouldn't be just limiting it to energy storage in terms of the ability to provide that service, so to speak. So someone mentioned carbon capture and storage, potentially. I think someone else mentioned earlier hydrogen, potentially as in power generation. So yeah, I think in general, some form of low carbon capacity or energy is going to be needed, and energy storage is one of those providers.
Yeah, and of course, energy storage is not just battery energy storage, but all portfolio for sure.
That's right.
Okay,
yes.
Great.
Adi.
Yes, go ahead, Pablo.
I'm sorry, I could not find my question box here. But anyway, I would like to have some comment, general comment, and a question for all speakers. Of course, all presentations were very interesting. It adds a lot of useful information, the different experience of every country. It's nice to see the concept of fully integrated element of REE that Belen brought to us, and also the several experiments of Terna, including some of them addressing more power servers and other energy. And the question of duration, very interesting results. And of course, also the experience that Bob discussed with us. And we can see that battery storage is a kind of Swiss arm knife, like was mentioned yesterday in the Australia session. The portfolio of service is amazing, and we are just discovering many of the powerful tools that battery storage can provide. Well, some authors already highlight that battery storage, not only battery, but energy storage as a whole, is a kind of fourth asset in the electric power business, because we are familiar with generation assets, transmissions, and distribution, but now we have energy storage. And we could see also the different sources of revenues that battery storage can allow. And I would like to see the comments from the speakers if in the regulatory framework we can foresee some kind of battery storage like concession service. In other words, a part of the transmission service, considering the benefits in terms of improvement of security of operation. I mentioned this because in Brazil, we had in the end of the last year authorization for the regulatory agency for a 30 megawatts of battery storage in the grid, considering the relevant benefits for the grid in a particular region. I'd like to see your comments about this.
I can go first, if that's okay. Yep.
Sure.
Can you hear me? Sorry. Yeah, I can go first. I think that would be a congestion product. Essentially, would be a really good solution in Ireland, if I'm looking just at this country, in terms of some of the issues we see for constrained areas of the network, and the difficulty in terms of historical difficulty in terms of building transmission network solutions, which have typically been grid reinforcements to alleviate network constraints. So looking at alternative solutions such as energy storage or demand-side response in constrained areas of the grid via congestion products is certainly something that we are looking at in Ireland. I think will be introduced in Ireland in the near term, and it is not only the essentially remunerating a service that the providers are paying for the grid, but also looking at ways of more strategically locating providers such as battery storage in areas of the grid, whether it's via network tariff signals or specific bilateral contracts via TSOs that can be offered to essentially provide alternative solutions to traditional network build. So that's something I think that should be on the table here, and I believe there will be a congestion product. So I definitely do see that as another service offering being opened up to energy storage in the future. Maybe some of the other panelists have comments too.
Well, yeah, I agree with you, and I would like to add that I think this is quite a quite new topic, and regulations should evolve, because at least in Spain we have some pending topics when talking about regulation, and yeah, from TSO's point of view, fully integrated elements as we have presented today is allowed, but then other functionalities for this kind of devices could require maybe well, market signals, and at the end that could be translated into a regulatory framework.
Well, thanks, Delenn and Bobby. I do not see any written questions. If there's any last comment or other questions, if you want to speak, please raise your hand. Otherwise, we will take a quick break until 10:20. So that's about 20 minutes for a quick breakfast or washroom or whatever you want to do. And then we will have two presentations for session C2. The first one by Jan, who will present on the development of battery energy storage systems in Germany. Following his presentation, we'll have a presentation from Brian from Fluence Europe. That's nice to see, in addition to Fluence US, which we've seen yesterday when it came to the North American perspective. Another last final Q&A session for this event, and that'll be it for this 2-day event. As I mentioned before, all presentation, slide decks, as well as recordings will be available to all CRE members, not just for transmission planners and operators. Any guest utilities or consultant that would like to require more information, please send an email either to myself at ari.kellenson@cre.com or programs@cre.com. So let's take a quick break, and I hope to see all of you in 20 minutes and start session C2. Thank you very much for the presenters, for ICP-Tech, and for your attendees for this interactive discussion. Really appreciate that.
Thank you, everyone.
So Jan Figner, I think we already tested your audio. Let's just do a quick test one more time.
Yes, I think
Here you
the
are.
audio should work. Do you hear me?
Yes, we can hear you. And
Perfect.
you will be able to share your screen soon. We will practice a little bit before just to make sure it's in full screen. Don't worry about it. And then Brian from Fluence Europe. For some reason, Brian, I cannot make you a panelist. I think it's because you're using a mobile device or a tablet. That's an interesting phenomenon that I recently learned, that there's no way to make panelists if using these devices. So what we'll do, Brian, is I will share my screen with your presentation, and you'll guide me and essentially tell me next slide, please, and that will solve that issue, okay? But let's see if I can hear you first, Brian. I'm trying to find you here in 70 attendees. Right. Brian, try to unmute yourself and speak. So it looks like your microphone is green. Maybe you have a hardware mute on your end. No, still cannot hear you for some reason, Brian. If you click on the audio tab, you could then select what kind of hardware devices you want the system to apply.
Hey, Ari, can you hear me?
Oh, now we can.
There you are. Hey, I took this on the walk, so I listened to the last speakers walking on my phone. I'm not intending to use this device, so
Okay.
I will. I'm back. I'm back at the house. I will be upstairs on my computer in about 10 minutes, and then we can test it then. Sorry to make you a little worried.
No problem. How was your experience using the mobile device? Is it working? Could you see it on the screen and everything?
Yeah, I could see the screen fine. I went on mute just to make sure I didn't accidentally unmute myself during a presenter's thing. So that was the reason it took a little while to switch off. But no, it worked fine. You could see the screen, hear everyone perfectly. It was great. Yeah, it took the last hour actually getting a little exercise. So it was nice.
Nice, that's good to know. As with all of these events, sometimes you tend to sit for a long time, so it's good to kind of walk and hear while doing other things. So thanks for sharing.
Exactly.
Cool. So still we have a break until 10:20. That leaves us another 15 minutes. I'm gonna grab a cup of coffee. Feel free to stay in here. Don't go anywhere, and we'll see you in 15 minutes. Thank you, guys.
Sounds good.
Hey, Salim, for those who joined late, currently we have a break until 10:20, so we'll start in 5 minutes, okay? Okay, so welcome everyone to session C2. My name is Ari Kellenson. I'm a program manager in CIADI Transmission Distribution. The next presentation will be by Jan Figner. Jan Figner studied electrical engineering and economics in Aachen and Istanbul. Since 2017, he has been working at the Institute of Power Electronics and Electrical Drives, as well as he initially was a project manager for monitoring the market and technology development of stationary battery storage. Since 2021, he has been head of the Grid Integration and Storage System Analyst Department. He's one of ISEA's representative in the German Energy Storage Association and advises national and international ministries, agencies, and companies. So Jan, welcome and thank you so much for supporting us with this event. I am gonna give you control in just a second. Here. And I hope I did a good job with your bio. I use LinkedIn, I believe. So if you have anything else to add, go for it. And you are currently muted as well.
Okay, yes, I just recognized this. Thanks for having me. Thanks for the introduction. And I will share my screen. Wait a second. So which screen?
Right now we see a desktop with 4 files.
Okay, then.
You can probably just drag the presentation onto this one if you want. Yeah.
Wait a second. I'm very sorry.
Yeah, no worries.
I cannot choose which monitor.
Let's try again. Maybe just a second.
Okay, so you see the slides here, right?
Yeah. Mm-hmm.
Okay, then I have to. Okay, so now you see it, right?
Now it's perfect.
Okay. Okay, so thank you very much for the introduction, and I'm very sorry for the technical difficulties, but from now on, I think we're good to go. So today I will speak about the development of battery storage systems in Germany, and to give you short information about the university where I work at. RWTH Aachen University is in the western part of Germany, and it's a quite large university. We have 50,000 students and about 6,000 scientists. I work at an institute that has 3 professors and about 150 scientists working there, so it's quite a large research group. We cover the whole value chain of batteries lifetime. So we start at the inner cell technologies like electrodes, electrolytes, aging, and cell testing. Then we have a unit that is responsible for pack design and BMS development and so on. And there's a second unit under Professor Sauer, which is focusing on grid integration of battery storage systems. And this is the section where I am working. This presentation is based on our publications. In case you find anything interesting, you can just download them for free. And I can already tell you that we're about to release the numbers for 2021 that will be uploaded on a preprint site in 1 or 2 weeks. So what are we talking about? The global battery storage market is really exploding. And this is from my colleagues from Bloomberg New Energy Finance, an outlook for the market development of the future. So starting in 2020 to 2035. And we see different areas of storage applications. The largest parts will for sure be private e-mobility as well as industrial e-mobility, and stationary storage, which is this small red one, will also be a part. So you see that the market will really grow strongly. And today I want to focus especially on the stationary market. So and this stationary market in Germany explicitly. To give a brief classification about storage systems, I just used a very simple one. I said everything below 30 kilowatt hours is home storage system. Then we have industrial storage, which should be from 30 kilowatt hours upwards, maybe to 1 megawatt hour. And then we speak about large scale storage, which is from 1 megawatt hour upwards. Many people in Germany already decide to buy a home storage system, mostly because they want to increase their self-sufficiency as well as their self-consumption. This is like one of the main motivations of the people buying these storage systems. But there's also a technical potential, because if you include home storage systems into the grid, you can include more PV systems, because the storage system is able to charge the PV generation, especially here in this high peak during the lunchtime, can charge it into the battery and thus decrease the feed-in power of the PV generation. So this is grid relieving. In Germany, there has been a large growth of storage systems. Here you see the numbers until 2020. It all started around 2013, when self-consumption became more economically more attractive than to feed in the power. And it was around 5,000 systems that were sold in 2013, and this increased dramatically until 2020 to 100,000. And I can already tell you that in 2021, it was even more, around 150,000 new installed storage systems. So we really come in a magnitude where the energy capacity and the power become important for the power grid. So here you see these numbers transverted into capacity and energy capacity and battery power. So by the end of 2020, we had over 2 gigawatt hours of home storage systems installed in Germany, with a cumulative power of over 1 gigawatts. And if you compare that to, for example, a national pumped hydro storage system, this is in the range of a very, like, already a large pumped hydro storage system. So this shows that even though the single systems are quite small, with 8.5 kilowatt hours and a power of approximately 5.6 kilowatts, you see that the pure mass of the system can still provide flexibility for the system. The prices of home storage systems have fallen down continuously since 2013. So when we look at a typical size of a home storage system, which is mostly from 5 to 15 kilowatt hours, we now focus on the section 5 kilowatt hours to 10 kilowatt hours, and we see the normalized system price over several years. So while in 2013 the prices have been 2,500 euros per kilowatt hour, they decreased by over 50%, and were by the end of 2019 at around 1,000 euro per kilowatt hour, where there are still at the moment also. Like there was not much of a price reduction. You can get cheaper systems, for example, from 600 to 800 euros per kilowatt hours, but it seems like the price decrease is not about to continue like the years before. And if we talk about home storage systems, we mainly talk about lithium-ion systems. That is about 98% of all systems sold. So these are just the prices for the lithium-ion storage systems. After talking about the home storage market, I would like to go into the industrial storage market. One motivation besides self-consumption, which we already saw with the home storage systems, is peak shaving. Peak shaving is the battery used in such a way that when there's a power peak, this power peak is provided by the battery. So in case you have different price tariffs for an industry side, for example, for power and for energy, you can reduce the prices for the power price, and then you can save money over the year, and therefore these battery systems are used. However, the industrial storage market is quite small at the moment. By the end of 2020, we had over around 1,500, 1,600 industrial storage systems registered in Germany, and the yearly addition in energy capacity and power is, in terms of energy capacity, around 40 to 45 megawatt hours. So compared to the nearly 1 gigawatt hour of home storage systems, this is quite small. And the power is around 20 megawatt. On this slide, you see the size of the systems. So most of the systems are below 100 kilowatt hours, from 30 to 100. So we mainly talk about small industrial storage systems, and as well as with the home storage market, all the systems are mainly lithium-ion. I'm very sorry, I'm just out of a COVID-19 infection, and my voice is really going down.
Yeah, no worries, Jan.
But I will take my time and come back. So you see that the large industrial sites, they don't opt for a storage system that often, but the smaller ones do, especially like small production sites that use machinery that have high currents, high powers. If they start, these can be used for peak shaving. And we also see, for example, supermarkets that want to have this green image and that want to increase the self-consumption. They also go for PV panels on the rooftop and then storage systems in the supermarket. In the future, we expect this by now quite small industrial storage market to grow. Because there are some main drivers. First of all, is decarbonization in the industrial sector. Like we have huge reduction objectives from I think it's around 30 to 40% until 2030, and so like these industry sites, they really have to install PV systems and use the battery storage for flexibility. On the other side, we really need to build more and more fast charging stations, because the number of electric vehicles grew way stronger than the number of charging stations. This is why the government have started an incentive program for building fast charging stations, and these fast charging stations will also need a buffer storage for peak shaving and for helping out with many EVs charging simultaneously in order to reduce the power that is drawn from the grid. So after we talked about the home storage market, which is really growing well, the small industrial storage market, we now go to the large scale storage market, which has in recent years been almost exclusively used for frequency containment reserve. Frequency containment reserve happens in a way that when there is too much load, then we have under frequency. So you need to discharge the battery in order to provide power. And when there's too much generation, we have over frequency, and then you need to draw power from the grid in order to stabilize the frequency at about 50 hertz. On the right-hand side, you see a frequency distribution over a whole year. Here you see the occurrence in percent on the y-axis over the frequency in hertz on the x-axis. And you can see that the deviation of frequency is quite small. So for most of the values, we're in the range of 49.95 hertz to 50.05 hertz. So that is a very small deviation. And most of these deviations are also in the dead band. This so-called dead band offers the possibility for battery storage operators to provide FCR if they want, but they don't have to. So most of the time they could also not provide it, but you can use, for example, the deadband to recharge the battery and for SOC management, because from time to time the SOC range comes into critical parts and then you have to recharge the battery again or to discharge it. So when there's under frequency, you have to discharge the battery, and when there's over frequency, you have to charge the battery. The prices for frequency containment reserve have been quite high in the years 2015 to 2016. This is why many projects were built during these years, which you see on the left-hand side. You see the cumulative number of large-scale storage systems, which rose from 5 in 2012 to about 70 by the end of 2019, and I can tell you that in 2020 and 2021, just a couple of new LSS were built. So the main years are over, and on the right-hand side, you see where these large-scale storage systems were used for. So as I told you, almost exclusively for frequency containment reserve. There were also some smart grid and renewable energy integration projects that were mainly research projects, and there are also some research projects about other grid services. When we transfer these numbers into the energy capacity and the power, you see these two figures. On the left-hand side, you see the cumulative capacity in megawatt hours. So by the end of 2019, there were about 600 megawatt hours. By the end of 2021, there were about 780 megawatt hours. And on the right-hand side, you see the power, which was by the end of 2019, 450 megawatts. And you also see that most of the systems are also lithium-ion systems, although we have the highest variety of battery technology in this large-scale storage market. However, in the last 2 years, it was exclusively lithium-ion that was built. Okay. So frequency containment reserve has not evolved as the operators of LSS storage system would have expected. On the right-hand side, you see the price development. You see the weekly price in euro per megawatt over the years 2008 until 2020. And while the price was quite high in 2015 with 3,500 euro per week and megawatt, this declined to about 1,000 euro per week and megawatt until the end of until 2020. Although we had a sharp rise in frequency containment reserve prices by the beginning of 2021, because all the energy prices were exploding due to the high costs while buying gas, we think that in the short term the prices may increase further, but in the long term there is not much potential for these prices being that high, because the frequency containment reserve market is only about 600 megawatts in Germany, and we have already that power of battery storage systems installed, and these large-scale storage systems, they are exclusively used for frequency containment reserve, and they don't have much of any other income streams. So that's why they have to go down with the prices in order to get that bid, and that is a development that is quite hard for economical operation. However, although this classical frequency containment reserve market is about to being done, there are two other things that emerge. The first one are so-called grid boosters. These are large-scale storage systems in the magnitude of 200 megawatts and megawatt hours. They are used for grid operation for the TSOs in order to reduce redispatch operations. And the other one are the so-called innovation auctions. So there is a subsidy, or there are auctions from the government where operators can bid for the combination of a PV system and or a wind farm in combination with a storage system. And there about the first 3 rounds brought about 250 megawatt hours into and about the same power. So yeah, there's still things going on in the utility storage market, and we're curious what the future brings. To give you a brief overlook about the development of electric vehicles, I brought this slide. On the left-hand side, you see the numbers of new registrations divided into battery electric vehicles and plug-in hybrid electric vehicles. And in 2020, we had about 3,500 350,000 new registrations, and that number doubled in 2021. And the energy is just massive compared to the stationary market. In 2020 alone, we had about 9 gigawatt hours of new battery energy in electric vehicles with AC power of about 3 gigawatts and DC charging power of over 10 gigawatts. And when you compare that to the stationary market, which was about 3 gigawatt hours in total by the end of 2020, you see that like this is where the music is really going on. Although, of course, we don't have the technical and regulatory framework now to use that flexibility potential that these EV would bring. But this will be solved in the future. So, for example, the European transmission operators, they announced that vehicle to grid will play a major role in the future energy system, and companies like Volkswagen really push forward the bidirectionality that is needed. And when you just think about that, only 3% of all the time a car is in motion, then it becomes clear that there's a huge flexibility that should be used for the energy system. So thank you very much for your attention, and again, sorry for my voice. I'm happy for questions.
Thank you so much, John, and don't worry about it. You did an excellent job. I am going to see if we have any questions from attendees. Yes, we have one question from Sask Power in Canada. So from a German experience, is there any limits or restrictions on the amount of PV plus battery storage generation on feeders to avoid the protection issues?
To avoid what?
Protection issues. So as you're adding, you know, PV plus battery storage in terms of the protection settings, or, you know, overall of the power system, I guess it can create some protection challenges or issues. So for that reason, is there any limits or restrictions when integrating that?
So the new government announced like very ambitious plans. They want to have new installations, for example, of PV of 20 gigawatts per year by the end of the 2020s. And like most of these will also be installed simultaneously with storage system. So I think to reach that limit, we have really a long way to go. And so I think if you just combine all the puzzle pieces with renewable energies, with seasonal storage through hydrogen storage systems, and all the other things you can do with the batteries, I think you can have a quite stable power grid, especially when you think that, for example, these vehicle capacities that we already have right now in the grid, but we cannot unlock. We could easily get rid of the pumped hydro storage systems, because there's so massive storage capacity. By the end of 2021, we had more storage capacity in batteries than in national pumped hydro systems. So I think like the integration of both renewable energies and batteries is really going on, and that's a very good development.
Thank you, Jan. A quick verification question. So what was again the percentage of homes with or with both BESS and renewable generation versus just renewable generation?
Okay, so right now, when you talk about new installations, it's about 60 to 70% of all PV systems being installed simultaneously within storage system. And when you have a look at the stock, this is not true because, of course, the PV movement started way earlier than the storage movement. And we have about 2 million PV systems right now in Germany installed, and about 430,000 home storage systems. So the percentage, like in terms of stock, is quite small, but with all the new installations, it's quite high.
Thank you, Jan. Follow-up question. How much did the grid peak increase by, just to get an idea of the diversity of a load factor? So how much did the grid peak increase was in your perspective?
How much did the grid peak?
Yeah.
Due to what?
Due to like EV integrations and all of these new loads that we've seen in recent years.
So the PV feed-in was, of course, in total was increased, but that is well handled, and the balance power is even going down has been going down for a couple of years. So that is nobody had expected it, but the primary control, like the frequency containment reserve market, is becoming smaller and smaller. And the grid is very stable. We have only a couple of minutes. I think it's 10 to 12 minutes per year and person. We don't have electricity. And if you want to have a look at the data, I can recommend to go on energycharts.de. This is hosted by Fraunhofer, and there you can see the instantaneous generation profile and load profile, and it's you don't see much peaks. Of course, you have to manage EV charging in the future. So we need to have smart algorithms controlling the charging, especially when the number of EV system increases as expected. But it's also very important to say that like the most common charging power for an EV will be below 4 kilowatts, because the average driver drives around 40 kilometers per day. And that is around, I don't know, maybe 5 to 8 kilowatt hours. And that can be charged with a normal power plug for like a small charging station below 4 kilowatts can be charged in 2 to 3 hours. So we don't expect like everybody to use fast charging. That will only be only be a problem for local fast charging stations, because I know, it's not like everybody cooks at the same time, because that's the same power, for example. So these things shouldn't be a problem.
Great. There's a couple of more questions from Ryan from Hydro Ottawa, Canada. So I'll let Ryan speak.
Sure, thanks, Ari. Yeah, so my earlier question about the electric vehicle chargers, that increase in chargers, how much did it add to the peak the grid peak, the normal grid peak? And are there any methods you are using to encourage charging off that peak? And then I have another question regarding vehicle to X.
Okay, so I'm very sorry, I cannot. I don't have any information about the. I think the influence on the whole energy grid is hasn't been seen. It's just for single charging stations that have problems with the grid integration, but the whole energy system is not affected in a bad way with electric vehicles right now. But we just have around 700,000 electric vehicles.
Nice. Okay. Vehicle to X is getting more and more attention. Now, technically, it's feasible, but practically, is it really feasible from a financial point of view and also from benefit to the grid when these are mobile? You don't know where they're going to be able to inject, whether they're going to be able to inject where you actually need them. And on the financials, again, it's the degradation to the battery, it's the layers of software, people along that chain that will skim a bit of profit. Does it really become viable financially?
So I think from a financial perspective, it's not that attractive. So from the calculations we did and what I find in literature, it's a couple of €100 per year and car. So this is not, especially when you this is just the income stream. If you have the costs, you calculate against it. This doesn't become very attractive from an economical perspective. When you consider battery aging, this is absolutely no problem because we talk about really small discharge cycles, and these cycles, they don't do any harm with a battery. We saw that in many test profiles we did with cells. We tested hundreds of cells, and these things are really no problem. You shouldn't care about battery aging. And taking a step back, maybe it becomes just a technical requirement for grid integration, so that a car has maybe to 5% of its power and capacity to reserve for the grid while charging or something like this. And this is also done with PV systems. They are just allowed to feed in maximum, like the small PV systems, maximum 70% of the power they have. So one could imagine to have this the system stabilization as a grid integration requirement. And in terms of you cannot be sure when are the cars where and when do they leave, is even in peak hours, there's not more than 10% of all cars simultaneously on the road. And 90% of the time a car stands still. Of course, not all cars are connected, but once the numbers become very large, I think it's quite fair to say, okay, with a security of 99.9%, we can ensure that we have that minimum power available all of the time. So I think it would be very very bad to not unlock this potential, as there's it would be from a whole perspective, it would be the best to use these batteries for for multi-use and so on.
John Salvesen, Technical Advisor, CIADI. There's a supplementary on that question. Would the car manufacturers not have to be involved? For example, I own a PV, but it's not capable of feeding back into the grid. It can take power from the grid, but it's not capable of reverse. And so somehow the manufacturer would have to be involved to produce cars that can feed both ways, and then everything that goes with it would have to be involved.
Yes, you're absolutely right. The key enabler will be the car manufacturers, but they really work on it. For example, Volkswagen announced that during this year, 2022, all of the MEB platform vehicles, like which are most of the Volkswagen brands, are capable of vehicle of bidirectionality, and they want to introduce a vehicle to home first and then vehicle to grid. By now, there are just, to my knowledge, a couple of bidirectional charging stations that are also quite expensive at the moment. However, when you just look at the materials used for charging stations, unidirectional and bidirectional charging stations, in the future, they shouldn't be much more expensive. Because there's just a couple of other or more elements you need to include, and then just think of about having a second car, for example, that stands most of the time at your home. So why would you need a home storage system if you could just charge the car and discharge it and use it as a storage system? But the only difference is that you have wheels on the storage system. So this is. I think when you pay about 10,000 euros for a storage system, which is a typical price, it's way more economic to go for an electric car where you pay, I don't know, 15 to 20,000 and use it for vehicle to home services.
Right. I completely agree with everything you say or said, and it's just a matter of the government and the regulators putting it in motion.
Yes, but they do. Like this is, of course, for the last years they said, okay, no vehicle to grid and nothing. But ENTSO-E has announced, has published a position paper where it says, in European transmission grids, vehicle to grid will play a major role. And I know that from the German TSOs, there are also committees working on new regulatory for these pools of batteries to join the markets. So it might be not too fast, but it's definitely coming. And the communication standardization is also people take also care of that. There's a new protocol which standardizes the communication for bidirectionality, and so I think not in the far future, but in the next couple of years, this will really be a thing.
Okay, thank you, Jan and John Sabiston for that. For the sake of time, we will move on to the next presenter. And Jan, if you can stick around after this presentation by Brian, we will have a final general Q&A, and we'll be able to address additional questions if any of our attendees will come up with that. So I'm just gonna take control here, and hello, Brian, we can see you. I'm just going to introduce you quickly and then give you control, if that's okay.
Perfect. You can hear me okay?
Yes, we can hear you. So welcome, Brian. Brian Perisou is a Vice President Sales and Market Development at Fluence. So he's been working on energy storage for more than 12 years and has held 6 different roles at the company, including his time as AES Energy Storage. Before his current role, Brian led the Americas sales organization at Fluence, where his team won more than 470 million of new orders, including some of the most innovative projects in the world. Brian also served as the lead of global strategic marketing and communications, which included all global marketing efforts, customer experience, product marketing, and brand development activities at the company. So Brian, thank you so much for joining us today, and we'll look forward for your presentation. I will hand you control in just a second.
Great. Good morning, good afternoon, everyone. All right, show my main screen. Let's do that. I'm going to do a share screen. Hopefully this all works.
Yeah, we can see it.
See the presentation mode?
Mm-hmm.
Perfect. All right. Well, I can't see you right now, but I guess that's all right. Let's see. Okay. I will go small there. Perfect. All right. So good afternoon. Good morning, everyone. Maybe start off with a little story here to start off or end the sessions we've had going on, I guess, the last 2 days. So last week, I was at my first energy storage conference in person in over 2 years. Now, you know, these online conferences and presentations, we learn a ton, right? They're really valuable. But there was something sort of unique and nice about being back in person, talking to real people about real issues we're trying to solve. It almost felt a little bit like we were going through sort of warp time, time warp. 2 years, the last 2 years kind of have stood still or flown by. It's sort of depending how you look, but it didn't drop a beat, right? As we were sort of talking, one of the things that was really interesting is the amount of sort of activity and buzz. The conference was in the UK, but there's people from all over, not just the UK, but Ireland, but all over Europe as well. But one of the things that's sort of been consistent from the very start is that every panel, every discussion, there's always a question raised. And the question is about the future capabilities of storage, right? As we go through here, we at Fluence and everyone on this call and everyone working in the industry, we're in the job of actually proving the impossible. When I first got into storage 12, 13 years ago, I was naive coming out of business school. I had an engineering background coming out of business school. I had assumed wrongly that all the stuff I was working on had been done, but I couldn't find any information on it. What we were doing was actually solving all of the problems at that time. What continues to come up? I sort of I don't know if any of you have sort of read the book Through the Looking Glass by Lewis Carroll. But there's an exchange between Alice and the White Queen where the Queen says, well, sometimes I believed as many as 6 impossible things before breakfast. So here's sort of a list of 6 impossible things that have come up over the last decade. And not only just over the last decade, but continue to come up, right? And it's in the conference we're in, it's in the markets we're in. And part of that, it's a sharing of information. These panels, these conferences are so incredibly important because it's an opportunity to share what's been happening out there and to build off the consistency. I've had the good fortune of being able to spend a lot of time around the world working on storage. As you said, I was leading the Americas sales organization. I was living in South America, so I've had the opportunity to work on projects in Chile and in Brazil, in the Americas, obviously throughout the United States and Canada, looking at projects in Dominican Republic and Mexico. And most recently over the last, I relocated to London not too long ago and have been working sort of in the European context and really the EMEA context for the last 8 or 9 months. And we still see the same questions, same issues. The difference is that it is a market that each country, even sort of sub-country, have very different sort of characteristics and sort of requirements. So here's sort of, we'll go through, and what I'd like to do today is we'll go through some of these and show some projects and talk through some of the things that were proven. The first one I think is always the best. Lithium-ion can never be connected to the electric grid, right? And to me, that's always sort of funny, but it was real. Those were the sort of first, for several years, it was impossible to connect lithium-ion to the grid. Then impossible to provide frequency regulation. I think we as an industry have killed these two, officially killed the first two, that they're no longer come up in conversations. But the next 4 still do, right? Storage can't provide inertia response or grid following capabilities. Storage really is just kind of a barnacle. It was always an interesting term. Solar, wind, hydro, they're doing their thing. They deliver clean, reliable, or clean energy. They don't need storage. It doesn't add value. Wow, were some of those wrong, right? Storage can never replace peaking power plants. There's still lots of questions. Is this possible? We still see open cycle gas turbines being proposed around the world, even though they don't make sense. Storage is not reliable enough to provide transmission services, right? Continue to see this one. And the latest, right, duration. We've heard it even in sort of the last few talks. Battery-based energy storage can't provide long duration storage. I think of long duration as 8 hours. You can think of it 10, 12, 14, 24 hours. I don't think of it as seasonal storage, but when you sort of look at that, but that's always the question as well. So I like to show this picture. I don't get to show it all that often. This is the impossible. Storage can never be connected to the grid. Really enjoyed Jan's conversation before this about vehicle to grid. VehiCLE-Grid, if you look at the project to the right, was the first project to ever allow and enable vehicle to grid. This takes us back to Pennsylvania in the United States. It was a 1 megawatt unit. The challenge at the time, there was a gentleman who was the CEO of PJM who said, I've got a bunch of electric vehicles, 10 or 12 electric vehicles sitting in Delaware, I can't connect them to the grid. They're technically able to do it, but the regulatory framework doesn't allow me. We said, we have a 1 megawatt battery, we can't connect to the grid. But the rule said if you have a 1 megawatt system collectively for vehicle to grid, you could connect to the grid and do vehicle to grid. So this was actually the first project back in the sort of the 2008 timeframe, 2009, that actually did vehicle to grid enablement, allowing Project Magic to be able to deliver VDG in the market in PJM. So sort of really cool sort of history. Fluence was founded in 2018. It brought together two companies, AES for the United States, Siemens from Germany. In 2018 came together to form Fluence. Fluence has had a story of its own. We've grown something like almost 10x in terms of number of people, number of markets. I think we're in 26, 28 markets around the world. Very active here, as you can see, throughout Europe. One of the things we pride ourselves on is really trying to focus on proving the impossible is possible, right? Looking and being the first in there. When the first projects came into Italy, or the first sort of projects came into Czech Republic or others, and it's not alone, right? We never take credit alone. There are so many players in this industry that have to go into working together to make these things happen, right? It starts with the political will. It starts with the technical and commercial teams at all of the grid operators that you're working with. It starts with, being able to permit these and the owners of the systems. I mean, every sort of project from the very beginning has, I don't know, 50 people who've really sort of enabled it to happen. But we pride ourselves in trying to find those people to work with, trying to enable them and trying to give them a sense of how storage has worked in their markets and how it could actually work in this market. One of the frameworks we use with Fluence, and some of you heard from my colleague yesterday, but one of the frameworks to really think about is applications, right? What can storage do in each of the markets? What's interesting about that is a lot of the applications, we've started very early where it didn't really matter the price of storage itself. Frequency regulation, some of the first projects in Chile, we were at $4,500 a megawatt hour, right? Just off the chart in terms of pricing on a megawatt hour basis, or on a kilowatt hour basis, sorry. $4,000 or $5,000 a kilowatt hour. But we knew that they could still make money, right? That was sort of the interesting part about them. As the costs come down, as the experience come down, as the technology improves, it unlocks these new applications. One of the sort of, it's been a while now, but in the solar industry, they've always had this, when did grid parity happen, right? At what point did solar become cheap enough that you could have unsubsidized solar in each market? It's been 15 years since I've read that report, and I still remember the bubbles, not exact where they fit, but really that concept. And to me, this is really sort of an insight about unlocking of applications within the different markets. And each market, and this is sort of where I think storage gets challenging, and you're hearing it through here, whether we're talking about in Germany, or whether we're talking about in Ireland, or whether we're talking about the UK, each of these have different sort of curves or sort of different applications that get unlocked as storage costs come down, as experience happen. But it's the framework that I think is so interesting. We're sort of pushing now, as we sort of went through some of these, and we'll walk through some examples and give you examples of each of the many of these within Europe. But we are now unlocking renewable integration and T&D enhancement, two sort of an incredibly valuable applications. Just before Jan was talking about the grid booster projects, which are a fascinating application for energy storage in Germany, and they're of the magnitude and size. They're 250 megawatt. I think combined they're either 350 or 450 megawatts combined between the systems. They're these enormous energy storage systems that unlock value within the system, really enhance reliability, particularly in markets where it's really difficult to get power from one side of the country to the other, or build new transmission lines. So as each of you, it sounds like we've got people from all over all over Americas and all over the world here. As you think about this sort of applications, which applications open up? Some of these have really strong depth, right, in terms of how big they are. Some of them are more sort of shallow, narrower, so they might only see they might see a saturation earlier, where others start to open up. So some of the first projects here in Europe. So this project is in the UK. This is a project with a company called Semcor. And what's really interesting about this was built starting in contract in 2018, built in starting in 19 going through. It's a portfolio of 4 sites. It's a 120 megawatt project. What's very interesting about the UK market, from my view, is that the services keep changing. You know, it's one of the few markets, if not the sort of only market where I know, where it's not just a change, you know, once or twice. I mean, this is a continuous changing process. So, you know, systems that we're providing what we call, firm frequency response, FFR, you know, all of a sudden there was a new service called dynamic containment that came in, and that dynamic containment enabled the systems to, you know, provide sort of a different service, whether it's a speed of response service or a sort of delivery sort of, well, speed of response really of there. But over the next 2 months, we're going to see 2 new services added in there. And the view is that these will continue to evolve. So they're sort of ever evolving markets as more and more storage and other resources are added to the system. It allows, you know, the operator to really get the most out of the systems. It makes it challenging for operators. It does make it challenging for developers and financiers. But because the depth of the market, because they've had this track record of building sort of capabilities, you're seeing an influx of assets really moving into the UK. And the projects now have gone from initial projects of, you know, 10, 12, 15 megawatts. This is a 120 megawatt portfolio, which was the biggest at its time. I mean, there was an announcement just recently from Intergen in the neighborhood of, I think it was 400 megawatt project, providing energy storage into sort of a, you know, as part of a capacity market within the UK. You know, going a little bit is one of the things I'm learning, right? Not only politically, culturally, but in terms of markets, each market is so distinct and different. You've really got to think about them by country and by market. And really the question on duration and you know, duration. We heard a lot about Ireland already, so I won't maybe hit all this here. This was one of the first projects. Give you a sense. This was actually the first project, I believe, into Ireland, providing the DS3 window and working with the system operator, working with Stockcraft, really trying to design the DS3's capabilities and how to test it, how to sort of understand its performance. The ultimate goal, there is a performance ratchet, or sort of the customer gets paid more for speed of response with a goal of 150 millisecond response on these. As we know, this, you know, the DS3 mechanism, as we know it, will sort of tailor off towards the end of 2024 with the goal of trying to find a replacement for DS3 and some of the other sort of capabilities within that market as well. You know, what's interesting, right? This is a 30-minute system, or just under 30-minute system. ESB in the same market has decided to move towards an entire, you know, to 2-hour system. So we heard a lot about duration, you know, the saturation of shorter duration systems, moving to longer duration systems here. And here is a photo of one of those actually installed, tested through the system with a 2-hour duration, right? And so what we're seeing is that customers are finding that, you know, trying to continue to find, I think we spend, I want to say half of our time, but we spend a significant amount of our time working with customers trying to find, should it be a 2-hour system? How do they think about revenue streams? How is their sort of capabilities to the system for a 2-hour versus 4 hours versus 8 hours? Or, you know, we typically, I'd say the most we typically will sort of work with customers on for projects today is about 6 hours. You know, you get the random request for 10, you know, 8 or 10, but most people today are sort of that 2 to 4, upwards of 6 hours of durations that they can find economically feasible in the near term, near to medium term. So these are really interesting to us and to the country because of the amount of capacity this provides into Dublin. There's some critical sort of load support needed in the Dublin area. We talked about constraints. That market is a very tight market, and really being able to provide sort of clean capacity and reliability inside that load pocket is an incredibly sort of beneficial area versus having to find other ways to manage that. As we sort of look at different markets as well, we you know, talked a little bit about the PCR market in Germany just before this. This is one of the projects that it's not a standalone PCR market, frequency regulation project in Germany, but it is one that's coupled with a hydro facility. And what I find very fascinating in some of the projects we've been working on in Chile, which have 5-hour capacity duration storage in Chile, is that while hydro is incredibly flexible, particularly dams and others, even run of the river is fairly flexible. This provides another level of flexibility. Unfortunately, through gas prices, through constraints, through others, we're seeing a lot of volatility in the markets. In the electricity markets, the rates are extremely high. Volatility is very high. And these sorts of storage assets provide a lot of extra flexibility, even when coupled with flexible assets. So it's not just storage with solar or storage with wind. We're actually seeing storage with hydro. And some of the areas we're seeing, run-of-the-river hydro that adds storage capacity of a certain duration, 4 hours, 5 hours, can actually get capacity credit and capacity payments in certain markets as well. That's more sort of common in South America than it is per se yet in the EMEA region. But that's sort of the trend we're seeing in certain markets. On that curve of new applications, one of the first projects, and I know it was on earlier, was one of the first applications was really trying to solve microgrids, right? We have diesel generators running in a number of markets around the world. One of the views I have is that there should never be diesel generators running, period. There's no point. You have storage, we have renewables, we have others. But how do we get to that point? And really one of the things that's interesting about sort of this is finding a way to optimize the use of that diesel generator. So instead of running, for reliability, you might have to turn on 2 generators at minimum load. Well, we all know that minimum load has a not as efficient set point. So you actually have a higher heat rate. You're burning more fuel. It has higher CO2 emissions, other emissions as well. If you can run just one of them at a more efficient set point, you can actually reduce just emissions by running the same amount and then using that backup reserve for using for storage, right? And so, these types of sort of, very innovative projects, this one in particular, I think ended up saving about 15% of the fuel savings on the island, about 55% reduction in the genset operating hours for there. That allows, the island of Entitoni and Italy to really drive. This project has been operating for, I'm gonna forget exact time, but I believe it's about 7 years or so. Don't quote me on that one, but it's been running for quite some time now, and it has sort of predated, came in from the days when Siemens was really looking at a lot of these markets as well, prior to Fluence. Some of the new ones, we now have several projects in the Azores and some of the islands off the coast of Portugal as well, where we've been working with customers like EDA, being able to provide energy storage. These projects, very similar, but on a broader, larger sort of island, are providing an amazing amount of sort of, regulation, allows sort of overall, flexibility of the system, resilience to the system as well. But, more importantly, in my view, right, it's cutting down emissions. We're limiting and decreasing, greenhouse gas emissions for running some of these diesel gensets, providing the island with more autonomy and the ability to sort of operate these incredibly beautiful places with a lot of the sort of clean capacity that's needed in these markets. And so, I know that the different islands all have goals of getting to 100% renewable, or the majority of them do in the near term, and storage ends up becoming a requirement to do that as well. And this is, we're seeing this in, I don't know if anyone's here from the Caribbean, others, but a lot of the Caribbean islands are really sort of pushing this too, because it makes such a incredible economic sense, but also from reliability and greenhouse gas emissions. And I think the last two sort of areas to touch on, as we're sort of coming up to my time, but is really, around this virtual transmission. To me, this is one of probably the most exciting areas where we're seeing storage deployed today as well. And really in Europe, I would say is taking one of the leadership roles here. We're seeing Germany taking a strong leadership role. Next project I'll talk about in Lithuania is just an incredible position. But what it allows you to do is to be able to add capacity to the transmission network without actually having to build more capacity. So a lot of this is sort of deferring new builds. It's allowing you to use instead of having, you know, one tower or two lines being N-1, allows you to put systems to allow more flow through those lines. You put backup, you could put backup on two different ends of the line, you could put backup sort of on the load side, or different. It really does vary by market. There's a lot of people who are much smarter than me doing all of the technical analysis on how to do this, the load flows, but the reliability requirements, the sort of capability requirements, it's another level of, you know, integration. These are, you know, for the most part, are network assets as well, and making sure that sort of the redundancies of controls, the sort of overall protection schemes, you know, we're connecting to 400 kV sort of, you know, substations and others. It's a whole nother set of sort of requirements. But that's sort of where some of our, you know, our founders, our parents from Siemens came from. And we have an, you know, sort of incredibly sort of strong and growing team really focused on this. You know, I think the last project to really look at, you know, I would say Lithuania has been really taking an advanced view there on how to integrate storage. The pictures here is actually of the first 1 megawatt deployment in the transmission network with Litgrid in Lithuania, focused on that. It's in operations, it's running, it's testing sort of a lot of the sort of pre-requirements to connect to the grid. They're looking at, you know, providing active power reserve, renewable integration, and some of these others. They have now announced, and we're building with them in partnership with them, 4 sites in Lithuania around sort of different substations that are going to provide very similar services to this as well. What that allows them to do is really provide sort of, you know, renewable integration, but it also then, as they start to synchronize with the European grid over the coming years, provides them the ability to sort of have that stable operations, the sort of fast response we were talking about, you know, millisecond response to the systems to enable that sort of synchronization to a new, to the sort of European grid. So another sort of, you know, it's sort of maybe an area that you wouldn't think of first in terms of storage. But what I've found too is that, you know, doing this, some of the places that are the most advanced are places you might not always think of. You know, the first storage projects, commercial storage projects, were the northern part of Chile. The biggest wind farm we ever built with storage was in West Virginia, United States. Lithuania has taken the lead for transmission. You know, storage as transmission. We will see that here now, a competition coming from Germany in particular to start to compete with something of this size. So with that, sort of last words, I guess, is, you know, our view is storage sits at the center of this, you know, complete transformation. It enables more renewables. We see it from you know, we see it from a curtailment perspective, we see it from a grid constraint perspective, but it also enables sort of more secure grids too. It's one of the first things that really got me excited about it. It provides sort of local capacity. It's not tied to any fuel, you know, so it's sort of multi-fuel, takes any electricity, it doesn't matter where it's connected. It has sort of, you know, it's zero emission sort of capacity sitting in the places you want it. So it really helps with climate change and other sort of, you know, electrical uncertainties too. So with that, I will turn it back over for questions. Thank you.
Thank you so much, Brian. Very interesting presentation, especially looking at the experience with Europe. I'll wait a little bit for attendees to raise their hands or type their questions using the questions box or chat. Panelists and speaker as well, please feel free to weigh in here if you have any questions for Brian. I have a question with regards to experience, maybe not in Europe, Brian, in Middle East or Africa that you could share with us, as you've been also involved in some interesting projects there, I believe.
Sure. You know, in sort of the two different markets, you know, the first place I ever got involved with storage was actually looking at rural electrification in Cameroon. So looking at solar and storage as a replacement for diesel generators back in 2008. It's actually what got me kind of the most excited about storage technology and the capabilities it had. And even in 2008, we saw that it was going to be cheaper. Solar and storage was cheaper and more reliable than diesel generator at that time. Unfortunately, we haven't built a lot of systems in Africa. There are more and more systems. We're seeing the announcements of PPAs. Markets like South Africa in particular is really starting to take off in terms of what we're seeing. Senegal is another area. We are seeing a lot of sort of mines, so sort of large mining, conglomerates looking at ways to reduce their uses of diesel as well. So it's an area that's starting to really become more interesting for areas. It is unfortunately not an area where we have been super active there, though we do have a team sort of looking at it and sort of prospecting some of the best. The Middle East, it's very interesting. We're seeing large amounts of solar go in, and in my view, it's only a matter of time before we sort of see a switch in really large amounts of storage. Now, there have been some of the largest storage projects announced in the market, but they aren't yet built.
Oh, that's good to know. Thanks, Brian. I do have a question from Shane Jing from Saskatoon Power, Canada. He's saying, hi, Brian, thanks for the presentation. I have a question regarding test of BESS before deployment. What is the common practice in Europe or North America in terms of test of BESS, PCS, PPC, etc.? What are your observation thoughts on this? Thanks. And Shane, there's a lot of acronyms. Sometimes I know them, sometimes I don't. If you want to just clarify, feel free to raise your hand and I'll be happy to unmute you so that you can ask directly. Brian, I hope you understood the question.
Yeah, I heard that too. I was waiting for him to see if he comes off mute, but
let's see. I think he's unmuted right now. Shane?
Yeah, can you hear me now?
Yeah, it's a little low. If you could just increase the volume or get closer to the microphone, that'll be great.
Hang on. Is it better now?
Yes. Thank you.
Okay, so basically, when before deployment, right, we want to test the battery, the whole system, make sure that it is performing as what we are expecting. So the battery itself, also there's a PCS, the converter, and also the PPC is the power plant controller, right? Those are all equipment combined together, building the system to use. So just wondering, Brian probably have a lot of experience with all kinds of different projects in Europe and North America. Just wondering what is Brian's observation in terms of, for those projects, usually how the utility has been testing those equipment or devices before, really energizing or put those equipment in service. And because that is an issue we are facing, right? Particularly, there's a lot of, say, PPC power plant controller. They usually is vendor proprietary, so it's a black box. So as a user for us, we don't really know what is exactly implemented inside, or what's the control logic internally. So we want to, have some confidence testing in terms of, before really spending the money, energizing it, and then we find the problems, and that's not good, right? So yeah, that's my question. Yeah. Thanks, Brian.
Perfect. No, it's a fantastic question. Areas, and it's an area that continues to evolve, I would say, where we see it. And so, as Fluence, we've been driving towards testing more of the system level integration before deployment in the field. So we've got 2 labs right now. We're opening up a 3rd one. So one in California, one in Germany, opening one up in Pittsburgh, Pennsylvania area to start to test, to continue to test at the system level. Because as you said, it's not just, it's one thing to connect, to test the sort of storage technology and sort of the enclosure capability, but then it's really looking at sort of that communication protocol to the PCS, but also PCS's capabilities, right? And if there's a firmware change on the PCS, or there's a change in the overall power plant controllers. So it really depends on the type of application we see. So I think for all applications, it's being tested, from Fluence at least, right, moving to the system level testing before deployments in the field. Not always the case, and not some of the older generations. You often sort of do testing in the field. When you're looking at frequency regulation or others, particularly when you've seen those tests before, and there's sort of standard protocols back and forth for communication, that happens. It happens sort of in the field. The ones where it gets interesting, particularly when you're on microgrid islands, when you're looking at black start capabilities as others, for certain projects, it's expensive, but it sort of on those sort of high advanced functionality, those actually get tested in the field or in the lab, running the simulations, both running the simulations and doing it with the hardware. And often the utility will come and check those tests, and it becomes a pre-requirement to deploy it on the grid. And so you start to catch some of the issues before they get deployed. I'd say that only tends to happen for those sort of high applications, or those sort of challenging applications that do have a lot more sort of interaction with the other parts of the system. Typically, though, I think if you're looking at, peaking or frequency regulation or spinning reserves or others in a more market, those typically will just have protocols that need to be tested as part of the commissioning process. So they'll, you go through a cold commissioning, then through a hot commissioning, then there is some equalization tests that happen and testing. So like in Ireland, there's something called the DS3 test, and so you have to run through. There's a very set protocol of what you have to test to, and then they sort of give you a certification that says yes, you've passed those tests as well. So hopefully that answered most of your question.
Yeah, thank you very much for the answer. Yeah, that's a lot of valuable information. Just a follow-up question. In your lab, when you're testing the battery and the PCS or PPC related equipment, so when you do simulation or test, do you guys say use some hardware in the loop testing, or just a sort of just a simulation basically? Just curious about what is done in your lab. Yeah.
You got me on this one. I don't want to misquote. I believe it is, but maybe we can, I'll connect with you offline.
Okay.
Or go through the organize, make sure I can get you that answer correctly.
Okay, cool. Yeah, thank you very much, Barry.
Shane Jean from Saskatoon Power, Canada. Thank you for your questions. I see there's another question from Gopiram. I hope I pronounced your name correctly. Gopiram, feel free to self-unmute and ask your questions, or if you prefer, I can read it for you. You should be able to speak right now. Looks like it doesn't work. Let me read this question on your behalf, Gopiram. So, with multiple installation experiences, have you noticed any early battery degradation issues raised with frequent and significant load changes? For example, every few minutes and every few seconds, etc.
Yeah, it's sort of a, probably one of the biggest areas of focus is on battery degradation and getting the performance there. I'd say, on some of the early assets, when changes happened in the frequency market, particularly sort of in the PJM, outside Europe, PJM Reg D market, there was a significant throughput change, which went from, I believe, around 1 cycle per day to like 3 point something plus cycles per day. And it had a material impact on degradation because of that change. We haven't seen that as much in other markets. There is becoming more sophisticated in how systems are contracted. I think, grid operators and others are understanding what a change in a signal or change in a market sort of, policy would do to those systems. What we are seeing, though, particularly in Europe, is compared to the United States, where there's a large PPA market, where there's sort of a fixed known quantity for what the storage would do, maybe there's a little bit of trading around or sort of area. A lot of the market in the UK, Ireland, and others has a very, well, at least in the UK and the Nordics, have a lot of merchant market, and they're really looking at how do I run the system to capture some of those sort of peaks and areas. So there is a lot of discussion around throughput. What we're seeing is that 2 cycles per day, sort of full depth of discharge, back-to-back cycles, is becoming sort of the higher end of requests. Now, customers will ask for 3 cycles a day, but the technology, there's a significant sort of, capacity reduction as you move to sort of that higher cycle, 2.5, 3 cycles and higher. So we are seeing 2 cycles today as, on these 1 to 2 hour systems as well in the market. And we aren't seeing material degradations, at those. There are some, some batteries and some that will, you find, like anything that's manufactured, you do have you know, not all equipment's perfect. So when you actually, you know, put in, we'll have to take some batteries out, replace them, you know, you'll find some and send it back for warranty, but on average, you know, they're performing really well. The projects in Chile, right, the first projects we put in Chile 2008 are still performing, still running, and still have a, haven't seen it in a long time and probably can't say, but are still performing well.
Well, thanks so much, Brian. Now it's a good opportunity for last questions for all speakers and panelists. Please come forward, share your camera to have some more interaction and discussions. Paolo, the team from ICPTech, Raed, John Savison, anybody who have general comments or questions. Same goes for attendees. If you'd like to be part of the, you know, this panel discussion, just raise your hand. I'll unmute you and we can take it from there. So this is an opportunity to ask questions for all speakers for today and over and above about the industry, the session, the project, anything that you might have on mind.
Adi, this is Paulo. I'd like to have a question for both speakers. First of all, thank you, Brian. Thank you, Jen, for excellent presentation. We have been just exchanging emails in the last 2 weeks, and I promise no additional requests from you. It's nice to hear both of you. I would like to ask something about possible barriers to introduce battery storage in the several regions and markets. For instance, the environmental side, what we can do with recycle or disposal. And I would like to hear if these represent a barrier in several countries that Brian has worked on, and also from Germany. And another question is related to possible barrier in countries like South America, where hydropower is strong. What you can highlight as a key differentiation from battery storage compared, for instance, with pumped hydro?
Sure. I guess I don't know if that's directed to me. I'm happy to answer both or go on. So on the recycling standpoint, there is actually a big push for recycling. You know, there's one of the challenges right now is not a lot of batteries have been coming off the line. So electric vehicles, you know, the charts we saw in terms of the sort of hockey stick coming from electric vehicles as well as grid, you know, those systems have been sort of deployed recently, or cars been started, but they haven't been coming off the line. So, you know, we're I don't know if we're a few years out, but we're just starting to see sort of those first line coming out towards recycling. There is a big push for recycling. Is here. I visited the recycling facility at Northvolt up in Sweden a few months ago and saw some of that. Northvolt has taken a very, very aggressive approach in terms of, you know, overall recycling content, both recycling of old batteries, not just theirs but others, but also putting it into the sort of input cell. As well, to drive out the CO2 emissions profile per battery to a point that it's less than 20%, I believe, of what you would get from some of the others. So Europe is doing a lot in that front. There is a European initiative for 2026 as well on some of the initiatives, you know, with sourcing of and recycling and others is a big part of that. Those initiatives. The hydropower, pumped hydro, you know, to me, we'll take every part of flexibility in the system we can get, right? As long as it's sort of clean, as long as it's flexible, I support every single kind that is there. We don't have enough in the system, or systems are fragile just in general around the world, and we need that flexibility. I think against pumped hydro, the biggest challenge is the environmental footprint you need to disturb to be able to build new pumped hydro facilities, and in that same footprint, well, in 1/100th of the footprint, you can do the same sort of, you know, same system on a megawatt basis. You might get 4 hours, you might get 8 hours. you won't be getting, you know, in my view, in the next few years, it won't be 36 or 40 hours. But a lot of systems don't need that. So it's really a footprint standpoint and the ability to build them. But if they can get built, if they, you know, the ones we have, let's continue to use them. If we can repower them or find other ways to increase their value, all for it.
Okay, maybe I can also share my point of view. Brian, that were fantastic answers, and I have the same points here. So you took most of what I was about to say, but maybe I can also do some to tell some further parts that came to my mind. First, let's talking about recycling. I'm completely with you that right now there's not just much coming back. Cars are sold, storage systems are sold, but they're still in operation, and what is coming back is not enough to have an economic feasible recycling. We do see very good recycling quotes with lead acid batteries, as they, of course, have a very, very large market share, for example, with starter batteries and so on. And this circular economy of lead acid batteries is quite far in already. However, lithium-ion batteries have different problems, because when we say, okay, lead acid and lithium ion, but when we actually talk about lithium ion, we talk about a couple of lithium ion families. We have nickel, manganese, cobalt, we have lithium iron phosphate, and even within these lithium ion sub-technologies, it really depends on the cell manufacturer what secret ingredients they put into the cells, which influence performance and lifetime. So you need big masses of the same manufacturer and the same production line in order to have automated processes. And a very big problem for recycling is that the batteries get cheaper and cheaper. So you get, for example, for lithium-ion batteries, you get metals out. That's all right. But when it comes to the lithium, first of all, there's just 1 to 3% of lithium included, and the quality of this lithium when you recycle is quite low. So it's probably hard to compete with new raw materials. So that's an issue. And so we're going to have to wait 10 to 15 years in order to have the magnitudes that we need for recycling structures in mass recycling in lithium-ion batteries. And before recycling, it's very important to think about a second life. But there's also a lot of problems with second life batteries, because when we just have a look at an electric car, it, for example, drives for 10 years, and then it maybe reaches a capacity, remaining capacity of 80%. So then people say, okay, 80%, that is most commonly defined as the end of life. So let's just put it in the home storage systems. And it sounds very, very romantic, but in fact, it isn't, because it's very difficult to deassemble a car, get out the battery, get it into a home storage system. Like every minute and every kilowatt hour of energy that goes into that process could be too much, because the new batteries have fallen in price 10 years. So the second life batteries would have to compete with the new batteries, which is very difficult, because when you have to put effort and time in it, of course it's also costly. And due to this pure economically perspective, you also have a technical problem, because all the battery packs and modules, they're not standardized. So it is very difficult to integrate them easily into home storage systems. You never know exactly about the aging of all cells. So you have warranty and issues, and with new certifications and so on. Like this is really a problem. So to me, like the most realistic way of a second life operation is just to find anybody that says, okay, I'm fine with a car that has 80%, and I'm gonna buy it. So that's for recycling. And pumped hydro is exactly what Brian said. So we can do everything with batteries. We just have to unlock the potential of, especially of electric vehicles, and to build more stationary storages.
Thanks, Brian and Jan. Kieran from Southern Company, would you like to join in? Oh, Julian, you'll go first, and then Kieran can go after. Go ahead, Julian.
Thanks, Ari. Thanks, Brian. Thanks, Jan. Very nice presentations. So for countries that don't have any storage, and no pump storage, no batteries, nothing. So for example, Brazil, we do ancillary service using the hydropower potential that we have. We have dams. 10% of the hydropower potential of the dam is wasted to generate electricity, and that makes no sense. Completely no sense. Of course, it makes sense to build storage capacity for ancillary services. But what in your opinion would be the minimum cost of energy to make sense in buy batteries to implement in Brazil to provide ancillary services?
I'll let Jan go first, and I'll take it, Jan, so I don't steal yours this time.
Okay, so you're asking for the minimal price of storage? Is that correct? I'm very sorry, because
no, the minimum price of electricity, because electricity in Brazil can be as low as 40 megawatts. 40 reals per megawatt. So that's $10 US per megawatt hour. So it can be very cheap when it's raining a lot, but when it gets dry, then it goes very expensive. But what's the minimum cost of electricity? Because you can waste electricity to provide ancillary services, which is what Brazil does. I don't agree with it, but that's what happens. But what's the minimum cost of electricity to afford a battery to provide ancillary services?
Okay, so when we talk about the electricity price, you probably mainly refer to arbitrage trading on the spot market. So this is very difficult to refinance a battery storage system, because you need very high spreads in order to buy when the price is low and to sell when the price is high. I haven't seen any calculations where just intraday trading is able to refinance a battery. However, of course, there are different prices in different markets. When we talk about the frequency containment reserve market, for example, there's no price for the energy that is provided, but there's just price for a power reserve guarantee. So, for example, you market 10 megawatts for right now in Germany 4 hours, and the amount of energy that you provide is not paid at all, but you get a capacity price, and that differs a lot from the spot market prices. So that really depends on the markets that there are in Brazil. For example, in the UK, there are even faster frequency restoration services than in Germany. So they have this ultra fast frequency response, and so on. And if the technology is able to fulfill these requirements, the prices can be very good. However, if there's a lot of batteries, the prices go down again. So I think the most important takeaway when it comes to business models with battery storage systems is to find a main purpose, which could be self-consumption, for example, or renewable energy integration, and then additionally serve several other markets, which is called multi-use. So when you just go for example, a home storage system, because that's very easy to go for. In the summer, you use it mainly for self-consumption. In the winter, there's not much sun, at least in Germany. So you could easily provide frequency containment reserve or whatever, or you use a car, and when you don't drive, you let an aggregator use the battery for services. So to have as much multi-use as possible and find a very good main purpose, and then add different value streams on it.
And I guess I would add, most markets storage starts with frequency regulation as the first entry point. But Brazil is actually one of those where it might not be, it isn't the first entry point and likely won't be, right? I think diesel replacements in Manaus and some of the areas in the jungle where running these large diesel generators where you're not looking at hydro at 40 reais per megawatt hour, you're looking at 300 or 400 reais per megawatt hour difference, right? I think that's one. I think, as Jan said, looking at sort of the applications there. But I think Brazil, Brazil is one of the more unique markets in the world because of the reserves of hydro, sort of that flexibility and the cheap. There are a few other markets in the world that have that, but Brazil is one. I think the big challenge though is really on low hydro years as well. Reliance on a single source of there, particularly when we're sitting in climate change, and we've seen some of the impact, I think maybe 5 or 6 years ago in Brazil with some of the really low hydros. The flexibility is lost when there's not enough water.
Thanks, Brian. Thanks, Jan.
Thank you, everyone. Question from Kieran, Southern Company. Go ahead.
So this is a question for Brian. Do you think the economics of lithium-ion batteries make sense beyond 8-hour duration, given that the EV market is more lucrative for the battery manufacturers compared to utility BESS? What are your thoughts on that?
Yeah, it's really the marginal benefit you get for that extra hour as you're looking at it is the sort of the way we think about it, right? And as the costs come down, there's more factories adding up. There's a temporary sort of, at least flattening of the cost decline right now we're seeing with a bunch of different things from the battery to shipping to all these other things as well. My viewpoint, is it will continue to increase in duration. I think over the next 5 years, 8 hours will become more normal. What it looks like 10 years from now, I think, I generally think it will be post more than 8 hours. What that ends up being. I think the anecdote I like to use is when we started this, we were building 15 to 20 minute systems 10 years ago, 12 years ago. I can now build a 5-hour system, right? So we're talking about 12 to 16 times more energy for less cost in today's dollars than we could back then in today's dollars. And so we see this sort of, multiple 16x increase in energy for the same price. We won't see that 16x increase in price, but we really only need to see a 2x or a 3x to start to really look interesting. So my view and sort of view company is lithium continues to be a driver for the next foreseeable future here, sort of call it 3 to 5 years. There are some really interesting other battery technologies that are under development. We've got a team really working on those, trying to figure out sort of at what point do they commercialize to give that sort of extra duration. But I think in the planning horizon, I think the challenge, right, is some people's planning horizons change. I think utilities obviously have to think 20, 30 years out there, and that's where it starts to get more challenging. But I wouldn't rule out 12, 16, 20 hour sort of batteries 10 years out. I don't think that's not a bet I would be willing to take.
Thanks, Brian. I hope that answered your question, Kieran. And I don't see any other questions or raised hands at this point. So now will be a good time to just mention that we have additional events upcoming from CIADI International. For those who are not familiar with us, you can check us out by clicking on this link or just Googling CIADI.com. We have fall events in person this time in the United States, predominantly covering different aspects. Climate change was mentioned earlier by Brian. That's actually a theme for our transmission and cross-functional event. Lots of different presentation on different themes, wildfire, reliability, monitoring on the environment, and so on and so forth. That's more or less it for me. I really enjoyed this 2 days event. Interesting presentation, different perspectives from all over the world. Really appreciate the support from the presenters today, from ICPTech for helping me hosting this meaningful event. If you have any questions or even comments you'd like to share with us, please send an email to either myself or program@ciadi.com. I'll be happy to answer any pending question as well as helping you network from one another. All presentations as well as recordings will be available on myciadeportal.com for all CIAD's members. You should be able to find it in a week or two, and that's more or less it for me. Any closing remarks from Paulo Barbosa, John Savistone before we wrap up?
My wrap-up, John Savistone here. My wrap-up comment is, wow. I learned a heck of a lot on last day, and it's incredible on how far we've gone with storage, and it's difficult to fathom what the grid might look like in 10 years with the technologies that are coming up. Like I was going to ask the panelists, well, what do you think the grid will look like in 10 years? And it's a difficult question, and basically the sky's the limit, and batteries will be the enabler, will be one of the enablers of this. So thanks a lot to all the panelists and the audience for taking it all in.
Thanks as well, John. Dr. Paulo Barbosa, quick closing remarks before we sign off.
Well, I also agree with John. It was an invaluable time of sharing learning during these days. And thanks to speakers and the active participation of the audience, and of course, to the CIATI team. We can see that battery storage is an open avenue of innovation and opportunities. Thank you all.
Thank you, everyone, once again. Have a great day or evening, wherever you are, and hopefully we'll see you soon. Take care now. Bye-bye.